Namaskar and welcome back to day 2 of Pincon. I'm Mamta Chinia, your host.
And I'm Manish Mishra, your co host.
We hope you had a fruitful networking session with the sponsors and exhibitors yesterday.
So, Mamta, yesterday we had interesting and informative sessions from speakers in technical symposia on cathodic protection and coatings.
Yes, Manish, and today is going to be even more interesting with 4 technical symposia lined up on inline inspection of pipelines, marine corrosion, corrosion monitoring and mitigation in CGD, and economics of corrosion, secure metal, insure capital.
We also have a special panel discussion on the topic corrosion education in India in the second half, which will be of special interest to the academia and industry.
And don't miss the special corrosion vodka spray in between.
And dear students, don't forget that NACE will be giving certificates of participation only upon successful completion of all the technical symposia.
So, without further ado, let's begin with the presentations on day 2, starting with the technical symposia on inline inspection of pipelines. We also have Mr. Anil Meghani and Srimati Nivedita Bhattacharya as technical expert panel who will be helping us in case of any technical glitch with the speaker.
All speakers may please note that you can see the controls to switch on your audio and video 5 minutes prior to your Q&A session, and the Q&A session shall be of 10 minutes after the presentation by the speaker.
Our first presenter for today is Mr. PRAKASH CHHAPOLIA. He is a specialist in data science, pattern analysis and classification. He is an electronics and communication engineer and is currently with Alethe Labs India Private Limited as manager projects.
He is going to present a paper titled ILI Feature Identification using Artificial Intelligence and Machine Learning Techniques. So, over to you, sir.
Greetings, everyone. I am Prakash CHHAPOLIA, Senior Data Analyst and Project Manager at Alethe Labs India Private Limited. As I'll be presenting a paper on how AI and ML techniques can be used to identify pipeline features and improve the process efficiency. Before starting, I would like to thank you, Pincon, and its organizers for accepting a paper and giving us an opportunity to present the solution on a global platform. I would also like to thank you, my team members, Varun Nidhi, Ravi Sharma, Sudeep Yadav, and all the people who have played an instrumental role in designing the solution. The topics that we shall be covering today is why pegging, what is the need of pegging in the pipeline industry. We shall have an overview of the pegging process and the MFL technology, how we manually analyze to detect the pipeline features, and how AI and ML process can be used to process the pegging data. Lastly, we would discuss the benefits of the AI over the manual process. We know the pipelines are the most cost-effective and safest mode of transporting oil and gas. Pipes are made of ferrous materials and are mostly underground, which also means it is prone to corrosion both internally as well as externally due to presence of chemicals in the soil as well as the product being transported, like water, hydrogen sulfide, carbon dioxide, bacteria. Corrosion reduces the lifespan of the pipeline. Operators cannot push the liquid over high pressure, resulting in the failure of the pipeline and loss of product. It is thus important to maintain the pipeline integrity, and operators need to do the pegging operations from time to time. In pegging process, a peg is launched from a launcher station. The peg travels throughout the stretch of the pipeline along with the flow of the liquid and is received at the receiving station. The peg is taken out at the receiver station and the data is downloaded and then analyzed. Pegs are generally of 3 technologies, which is magnetic flux linkage, also known as MFL, ultrasonic transducer or UT, and electromagnetic acoustic transducer or EMAT technologies. MFL is the oldest and most widely used ILI technology. MFL PIGs have powerful magnets and multiple Hall effect sensors installed between the magnets. It works on the principle of physics where the pipe material is magnetized beyond the saturation level. When a feature is encountered, the flux leakage is detected or captured by the Hall effect sensors and saved in a local storage. The data captured from the flux leakage forms a pattern which is specific to a feature, also known as feature signatures. On receiving the data, on receiving the PIG, all data is downloaded and then analyzed for the features and corrosions. The data downloaded from the PIG are in terms of hundreds of GBs. The data are recorded in multiple bin files and is distributed to a team of 10 to 12 operators. They go through the complete data set and analyze the flux signatures and the grayscale images from the MFL signals. And the features are noted down in Excel sheets. The data downloaded from the PIG is in terms of hundreds of GBs. The data is recorded in multiple binary files and is distributed to a team of operators of 10 to 12 people. They go through the complete data and analyze the flux signatures and the grayscale pipe images and note down the location and sizing in an Excel file. A final file of all CD is compiled, which is equivalent to the pipe tally. Manual process has its own limitations, like high analysis time, human biasing, features getting missed, and many more. When we talk about AI, artificial intelligence is a division of computer science in which computers are trained to work like human brain. It makes possible for computers to take decisions based on the data like a human brain does. So machines are trained to identify different features, including corrosions. Features with high prevalence like welds, corrosions, sleeves, flanges can be detected using AI. Features with low prevalences are initially detected using a rule-based approach, and when we have a good quantity is being moved to a AI approach. Here we can see that AI model, we have two images, one representing AI model and the other representing a human neuron cell. An AI model is a multi-layered approach consisting of a convolution and pooling layer, which actually acts as a feature or properties generation layer for the input image. The properties generated are passed to a dense network consisting of multiple interconnected neurons, which then gives a classification of the features. The neurons in the AI model act exactly as the neurons in the human brain, where there are different dendrites in the human cell, which collects the information from different dendrites, does an analysis, and then we have a synapse which takes a decision and then provides the output on the axial terminal. Similarly, in the AI model, the individual neurons captures the data. Individual neurons are interconnected to each other based on the features generated from the pooling and convolution and pooling layers. Different features are then classified and an output is being given either as weld, sleeve, flange, or a metal loss. The AI also needs to be trained just like a human brain. So the first step to do AI modeling is collection of data, and understanding of the data. For this, the client has provided us bin file along with a list of verified features of the data that we have used in the training. The data from the pig contains information collected from the Hall effect sensors, odometers, gyro, sanity, and other sensors. All the data are extracted individually from the binary files, decoded from hex to the desired format. Like for Hall effect sensors, the hex data are converted to MFL signals. For odometers, the hex data is converted to odometer signals, and so on. Once the data is extracted, the required data is then moved to a denoising sequencing. The data captured from the pig is while the pig is in motion. That means there is some induced noise in the data itself. The noise could be because of the electronic itself or the external factors like ununiform pipe material, vibration of the pig, or sensor liftoff. The data is captured while the pig is in motion, which means there would be induced noise in the data. The noise could be because of the electronic itself or the external factors like ununiform pipeline material, vibration of the pig, or due to sensor liftoff. To remove the noise, techniques were developed based on hardware electronics methods, which includes development of low pass, high pass, and wavelet filters. Once the data is processed through different layers of filters, we have filtered and smoothened data, which can also be seen in the coming slide in form of images. So this is an image of the raw data where we can see, where we cannot identify the type of pipeline, even any features, if they are present in this section of the pipe. Once we have done the filtering of the data, we can see it's a spiral pipe with some features present on the pipe itself, and similarly in the heat map as well. A smoothened image is more clear with respect to the features of the pipeline. The features needs to be trained in the model so that model can identify and classify those features. For this, the client had already provided us a verified feature sheet. The sheet had an ample amount of data for welds, sleeves, and other features, but was having a limited quantity in terms of corrosion and metal loss. For AI to work, we needed a very good quantity of features so that the results would be good. So we developed a technique which worked on the real defects, and using the technique, we created many virtual defects in terms of thousands of virtual defects. These virtual defects were used for training the model. 80% of the virtual defects was used for training the model, and 20% was used for testing the model. Once the model was trained and testing was done on the 20% of the data, the results were analyzed by the operators manually, both in grayscale as well as in signals. Initial results had a high prevalence of false positives, true positives, false negatives, and true negatives. The verified data, the feedback from the operators was captured, and then it was augmented to the training data.
What did you do? Change karo. Sorry, there was a technical glitch.
And the model was retrained. With continuous monitoring and feedback, we were able to achieve a very good efficiency, detect 95% of the metal losses in the complete run, and reduce considerable amount of false positive, thus increasing increasing the accuracy of the model. This is a sample output from the AI model where we can see different features along with its location, log distance, and the characteristics of the features. The features, individual features can also be verified in form of images where we can see proper annotations respect to the features both in grayscale and heat map. The same can be viewed in the smoothened image as well, which really helps the operator to cross-verify the results of the AI engine. When we talk about the reporting module of the AI engine, it has numerous reports, both graphical as well as tubular. The engine supports multiple pic sizes, right from 12-inch to 48 inches, and the reports can be exported into different formats. The operators can directly pull out different reports once the analysis is done. Reports like pipe tally reports, location information sheets, list of anomalies and components, metal loss distribution, percentage wall loss, etc., and many more can be generated. This is a sample pipe tally report from the system where the operator can directly generate the report, give it to the field team or the pipeline division to verify the features or for record purpose. The pipe tally is almost to the PO specifications and meets most of the requirements. When we talk about benefits of AI over manual process, there are numerous. Just to summarize, the AI process reduces human dependencies. That means it reduces retention, monitoring, as well as the training process of the human. It is able to detect small defects which are generally missed during human analysis. It helps in corrosion growth profiling, which provides insights on effectiveness of corrosion.
Thank you so much, Mr. Prakash, for the presentation. Can we have you on the screen, sir? Mr. Prakash. Are you there, sir? Mr. Prakash is trying to switch on his audio. We'll just wait for a couple of minutes. Yeah.
I am there online.
Yeah. Hello, sir. How are you?
I am fine. What about you?
Good, sir. Nice to see you, sir. Excellent presentation.
Thank you.
There are certain questions on the chat box, sir. Do you want me to take the questions, sir?
Yeah, sure.
Just a minute, sir. Yeah, sir. The first question is, as you remarked that high number of defects are required for analysis of IP data, does that mean that AI analysis will be more effective than IP survey of older pipelines?
See, means in AI, mostly when we talk about AI analysis and human brain, it's a similar process where we need to generate proper features to identify a particular category. Means if it's a corrosion, we need a good amount of data with different sizes and different percentage of wall loss so that a different set of corrosions can be identified and classified. So for any feature that needs to be classified, a good amount of data has to be present so that a proper training could be done and the results can be detected by the AI.
Okay. The second question is, sir, is this same as feature boxing that occurs in traditional ILI software analysis?
Yeah, means like when we say about the feature boxing is required so that we can identify the boundaries of the feature, say for corrosion, to identify the depth, the length, and the width of the corrosion. We need to have a feature boundary The training data should have a feature boundary so that the AI engine can also work similarly and define a feature boundary and generate a particular image or a particular size of the feature. So a boundary definition is required for training as well as for identification of the feature.
Okay, sir. The next question is, sir, which technologies are used in pigging for pipeline integrity assessment?
So pipeline integrity assessment is all totally a different technology when we say about a corrosion management or something where we need ICDA direct assessment or different technologies are there which is a secondary step over the AI. Once we have a pipe tally data, the data can be merged with other data, say corrosion analysis data from that we have from cathodic tools or from internal corrosion direct data and all. So those data can be merged together and then a pipeline assessment, integrity assessment could be done. AI or the pigging operation is just a part of the integrity assessment.
Okay, sir. The next question that we have over here is, what is the accuracy level in AI technique?
The accuracy level in the AI technique, when we define in the AI technique, the accuracy level that we have obtained with is like 95% to the field runs, means when we verify the actual result of the AI with the field with a manual analysis, we have achieved a 95% accuracy with respect to the field verifications.
Okay, sir. The next question that we have over here is, what are the advantages of AI technique over ILI technique?
When we talk about AI techniques over ILI techniques, the ILI is mostly, if we talk about like physics-based techniques for ILI analysis, it's mostly based on signal analysis, which could be a manual process. When we talk about AI is a kind of hybrid model which works both on hardware, means which works both on physics models as well as an AI engine which gets trained over the analysis of the data or the pattern of the data over a historical data that I would rather say. Physics model works mostly on the signal patterns. AI works on signal patterns as well as a historical pattern which presents a growth analysis or a prediction kind of that what kind of metal loss this could be or what could be if this could become a metal loss or not.
Okay, sir. One last question, sir, that we have over here is, has it been implemented in any pipelines in India, and what are the difficulties faced in it?
Yeah, it had been implemented in one of the largest operators in India, and they are using it very well. And difficulties, like whenever we talk of AI, obviously the biggest difficulty is the data collection, understanding of the data, extraction of the data, and tuning the model. So when we say like data collection for working in deep learning technologies, we need to have a good quantity of data with a proper data set and a uniform standard so that the AI engine can work, AI engine can learn the pattern and can identify different features in the pipeline. So the client had that much amount of data. We were able to get the data, we were able to train the data, and we were able to provide the results to meet the expectations of the industry.
Right, sir. Thank you so much for your time, sir. Excellent presentation, and we really have very happy to have you over here, sir. Thank you.
Thank you. Thank
Thank
you
you.
very much.
Bye bye, sir. Have a great day.
Bye-bye. Thank you.
Our next speaker for the day is Mr. Jason Edwards, who is a project manager at ROSEN. He is a mechanical engineer with specialization in ILI within material properties and integrity management.
He's going to present the paper titled "A Material Verification Process Within FFP Assessments." So over to you, Mr. Jason Edwards.
Hi, my name's Jason Edwards, and today I'm going to be presenting about a material verification process within FFP assessments. So this is just a little bit about me. I'm project manager by ROSEN, and my area of specialization was within INLINE, specifically around material properties and integrity management. But I won't talk too much about myself. Let's move on to the presentation then. So this is just a little bit of an overview of what I want to talk to you about today. And it's really centered around this material verification framework. And firstly, I want to talk about, why this is important to establish material properties. And when I talk about material properties, I want to talk about pipe grade and toughness. And then secondly, I want to talk about, what is the material verification framework? And we throw some words around here like enhanced ILI and NDT and pipeline DNA process, and I'll go through these a little bit later. And thirdly, most importantly, how we're using this material verification framework to really help operators around the world to firstly, establish a robust knowledge of material properties, and secondly, how they can use this as input in integrity assessments such as FFP assessments and MOP reconfirmation. So this first slide is really just about the importance of materials data. And when I talk about materials properties, the two I want to focus on is really pipe grade and toughness, right? And these really sit on the same level as the key components of integrity management, such as integrity threats, operating conditions, wall thickness, pipeline route, and seam type, right? And these two properties really form the foundation of our integrity management. And when I talk about integrity management, I talk about MOP, and that's really defined by our diameter, wall thickness, and once again, pipe grade, right? And when we look at fitness for service assessments, assessment of metal loss features and assessment of crack-like features really depends on, your pipe grade as well as your fracture toughness, right? And when we look to the future of, hydrogen conversion to hydrogen service, different pipe grades of materials may have different susceptibility to hydrogen-assisted cracking or embrittlement. So, these material properties are really, really important. And without a robust understanding of these material properties, we can't really start to make informed integrity decisions. So pipeline records and how good are yours? And this chart really highlights, the ranging confidence levels that we see between different operators around the world. On the left here, we have no records, unsafe operation, and a high risk. And we want to move down this chart to get to full traceability on every single component. And there we have a low risk, right? And typically what we found, most of the operators sit somewhere in the middle here, where they have a fairly good understanding of the design concept, right through to a lot of good detailed information about pressure test records and mill certificates, right? But the question always remains, do you have full traceability on every single component, every single pipe or spool that has been laid? So even though we think we may have good records, things can always get missed, right? Gaps within the processes start to appear, especially as operators change hands or new owners come in, new service providers come in. We see this breakdown of processes and we see traceability of crews and documentations of replacements cannot be as good, right? And really, are your records being updated correctly, right? So this all leads to this unknown unknowns, and this is what I really want to kind of cover today. So why are material factors often not addressed? The first one is really practicality. Where do you start? You may have hundreds of kilometers of pipelines and 10,000 plus individual pipes, right? Cost as well. The cost of excavations is really expensive, right? And a lot of these locations are in not easily accessible locations under roads, rivers, environmentally sensitive areas, right? Limited solutions. Traditionally, the way of obtaining material properties is to conduct, destructive testing on cutouts and coupons, right? So this can become quite expensive and obviously time consuming. And the last one is know-how. What exactly do I need to do and where, and what material properties do I need and what do I need them for? So previously these four factors were often a stopper. But with new ILI and NDT methods available on the market, we're now able to address a lot of these issues that have been, previously both prohibitive in terms of complexity and cost. And so when we look at ILI, ILI can really provide material property data on every single joint and really reduce the amount of excavations necessary, right? And then we also look at new non-destructive techniques that are able to measure pipe strength. And lastly is really the know-how, and it's really around, you know, a structured but flexible material property framework that we can adjust to suit the needs of the operator. And so this is what I really want to talk to you today about. So this is what we've been developing over the last 4 or 5 years, this material verification framework, and this is what I'm going to talk to you over the next few slides. And it's really around, you know, first step is really inline inspection, right? And this is where we want to gather data on material properties and defect anomalies, right? Step 2 and 3 is really, you know, step 2 and 3 go together. Step 2 is pipeline DNA. And this is where we really want to define the populations and associated material properties, right? And I'll go through what that means later. And step 3 is you know, interrogation of existing records and in-field inspection. And it's really material verification to verify the properties and gain confidence within our data integration and pipeline DNA process. And lastly, we have step 4, which is all our integrity assessments. So it's our FFP assessments, it's our ECAs, and I'll go through some case studies about, you know, how we've done this for operators. So enhanced ILI. You know, what is enhanced ILI? It's really just obtaining material properties and defect anomaly data through ILI, right? And for us, it's really centered around this ROMAT pipe grade sensor as what we call it here. And this really provides us this critical data set, you know, pipe grade or yield strength, that links all the different material properties across all the different feature detection technologies. And we can incorporate this into a single MFL tool setup or ILI tool, and it allows us to capture 4 data sets within one inspection, right? We get the ROMAT PGS, which is the pipe grade. We get our metal loss here. We get our deformation here, and we get our XYZ mapping, right? And by really integrating these data sets, we use this process called the pipeline DNA evaluation process, and it really to provide us a reliable population approach that can identify differences in pipe properties and attributes down to the individual pipe or component level. And I'll go through that in the next few slides. But additionally, by, you know, combining this with other data sets such as crack and hard spot detection technologies, you know, we're able to gain an extra level of detail with that allows us to increase the confidence within the population assessment, as well as provide, you know, information on the different defects that really exist within our line, which are really critical inputs into our FFP assessments. So pipeline DNA process and what is it, right? And it really is about defining the populations. And so a population refers to a group of pipes with the same grade, wall thickness, manufacture process, and manufacturing or construction date. An example of that is really just a batch of pipes from a mill with a consistent manufacturing process, right? And what we do is we interrogate all the different data sets collected from INLINE, with yield strength being this key defining factor. And by analyzing, you know, your wall strength or the strength distributions and combining it with other known pipeline characteristics like your wall strength, wall thickness, sorry, diameter, pipe type, and joint length, you know, we're then able to define these individual populations of pipe. And I'll show you what I mean here. So this is really defining the populations using strength and assigning a grade. And here, in this diagram here, you can see yield strength on the left here, and that's log distance on the bottom there. And here we have the 2 different colors. So we have this orange color here and this blue color here. The orange color is really just, these are 2 different populations, what we call it. And each pipe is given an individual yield strength value. And we really look at the distribution of yield strength as a whole across the entire population here. And when we start to analyze these distributions, we can start to pull out individual populations, and we can see that, you know, this orange here was actually a replacement or a rerouting around a new development. And you can see it's designated by a different yield strength, right? And when we overlay it with the XYZ mapping, we can start to see this really clearly, right? And when we look at this distribution of yield strength, it's described by this normal distribution, right? And when we go ahead and define a grade, we don't use the average or the mean. We use basically 3 standard deviations away from the mean. So we use a conservative approach where majority of the pipes would meet this minimum requirement of X56. So really, this is just really the output of the pipeline DNA process. There's a lot going on here, but basically each of these colors or symbols represents an individual population, right? And you can start to see this is your pipe yield strength once again versus log distance of the entire entire length of the pipeline. And each of these populations is defined here. And we assign each population, obviously a number. You've got your total length, your number of pipe lengths, your assigned grade, your pipe type, and a description. So each individual population has its unique characteristics, and these are defined within the pipeline DNA process. When we start to look at this blue population here, we would call that something called the main population, which is typically your original construction. And we start to define that as grade X52. And then we can start to look at, pull out these individual populations, and we see that population D2 is a highway crossing, usually designated by a higher yield strength, and we can see that. And then we can start to pull out all these individual populations here and assign a grade and define the characteristics for these. So step 3, in order to really verify and validate the data from the DNA process, we really need to conduct material verification through both destructive and non-destructive testing. So traditional methods of strength determination are to remove coupons and conduct destructive testing, but this can be often expensive, time-consuming, and dangerous, right? So there are new NDT methods out on the market for determining strength. These are IIT and MMT. And these allow us 2 things, right? Allow us to measure the strength of the tighter tolerance and confidence in ILI, validating our PGS tool. But secondly, they provide more accurate inputs into the DNA process, right? Fracture toughness is another one, and currently there's no commercially available NDT technique for determining fracture toughness, so you can only still do that from destructive testing. And then the other 2 are chemical composition and surface metallographic imaging, right? And these 2 really tell us info on the different vintages of pipes, the pipe maker, and the pipe manufacturing process. And these can really tell us a lot about the characteristics of the populations and if we can combine certain populations together and match up with our records. So refining the pipeline DNA. So INLINE is really used to produce this first initial pipeline DNA, right? But as we, gather more records, conduct more in-field testing, right? We continually refine the pipeline DNA. We're able to really characterize the populations in more detail, and we're really able to start to build the detail within our pipeline DNA. And as more data really comes available, we can combine or separate certain populations out. So it's really an iterative process which starts with ILI and continues on for the years to come. So step 4, the good stuff, MAP reconfirmation and input into FFP assessments. How is this really going to benefit you in your integrity decisions, right? So this is just a case study here. Basically, we identified a population of pipe that was not known to the operator. As you can see here, we've got a SMYS of X42 here. And basically, through the pipeline DNA process, we identified this population of pipe was actually below the SMYS. And this was confirmed through some in situ non-destructive testing. And once this was confirmed, the operator put in a replacement program to replace these population of pipe, right? So case study number 2. Once again, we have this pipe yield strength on the left and log distance, which you've seen quite often. This particular operator had 2 different manufacturers or 2 different populations, but the traceability for these populations had been lost. The operator didn't know exactly where these populations sat on their pipeline. So when we ran the pipeline, when we ran our ROMAP PGS tool and did the pipeline DNA processes, we found we could clearly see the two different populations that the operator was interested in. We can clearly see that they were differentiated by this yield strength, right? All the other characteristics of wall thickness, pipe joint length, and diameter were the same, but the differing factor was this yield strength, and we could clearly pull this out and start to define, exactly where this population sat within the pipeline and exactly what were the characteristics of this population. Case study number 3. So input into assessment of crack-like anomalies. So this particular operator experienced a pipeline leak due to cracking within a hard spot. And as you can see here, we have zoomed in versions of the microstructure. And basically we ran a number of ILI services for this operator, ROMAT PGS as well as metal loss, crack, hard spot detection, really in an effort to aid this MOP reconfirmation. So we actually had cutouts from this failed section here, so we were able to conduct some fracture toughness testing on this. We also conducted chemical analysis, tensile testing, and some Sharpie impact testing on these sections as well. So all this testing really helped us within the, firstly the material verification process, as well as input into the FFP assessments in the end. And I'll go through that a little bit later. So really for this is once again the population overview, and really material verification was used as an essential first step to really define these populations, right? And by running enhanced ILI, we were able to get an overview of all the defects in the line and which populations they're occurring on. And as you can see here, we have this orange and blue, A1 and B1, right? And these really make up 90% of the line. And about 60% of the cracks were within these two main populations, right? So when we start to overlay all these defects onto our populations, we can start to see if there's cracking in a particular population or location along the line. We can also see if there's, overlay cracking defects against other defects, and we can start to see hard spots or dents in cracks, which are immediate threats. So really this overview is so that we can really define the material properties for each population for input into the FFP, as well as define areas of interest that we may want to carry out, in-ditch verification on. So there may be populations where we need more material properties or particular defects of interest, right? So in-ditch verification plan. This is really important so that we can define a dig so we can hit multiple locations or multiple populations in one dig. So within this, we were able to choose 4 dig locations and hit 7 different populations within this. As well as, line them up with particular features of interest. So in this particular dig location, we had 3 populations, and one of the populations or one of the areas of interest had a crack. So we were able to really assess this crack and actually verify that there is a crack there as well. So defining your locations for material verification is really important first step, right? And once again, we have this population A1 and B1, which the majority of the defects were on. So defining and verifying these populations is really critical. And so when we looked into the chemistries of both A1 and B1, we found that they were very similar. And from this, we were able to use the fracture toughness values that we had for population A1. We're able to use them within our FFP assessments for population B1. So this really helped us to avoid using really conservative fracture toughness values for population B1. So a bit of a summary of the results of the FFP assessment, but what I want to focus on here is just really the benefits of the material verification process. And it was really around optimizing your material verification plan. We were able to carry out, verification on 7 different populations with only 4 digs. And the second one here is verifying the material properties of the different populations within the line, right? And that's really critical for the input into the FFP assessments. But the most important one here was really able to assess the majority of the defects with representative or representative material properties, i.e. fracture toughness values, right? And this really allowed us to limit the amount of unnecessary repairs due to any conservative assumptions of fracture toughness that may have been used within this crack assessment here. So in concluding today, just a bit of a summary about what I've covered today. And it's really just around this integrated approach of enhanced ILI and integrity solutions, which we've been coming up with at ROSEN here. And it really allows operators to gain this clear picture of the pipeline DNA of the entire pipeline from just a single one-time inspection, and you really get this big overview of your populations and pipe grade there. And then from there, you can do your material verification. And one of the outputs of that is really to identify, direct integrity threats from unknown populations or understrength pipes, or anything that you're particularly interested in. And this really underpins the material properties really forms a foundation for these integrity management applications, such as fitness for service assessments, MOP validation, or conversion to hydrogen service. And the foundation, we base a lot of our decisions on material properties, and it's really ensuring that we have a robust understanding of these material properties before we go ahead and make all these integrity decisions. So that's my presentation today. Thank you for joining, and now I think we'll go on to the question and answer session.
जो 10:30 के बाद सर आने वाला है ना,
Mr. Edwards, for your presentation.
फिर सर
We have received questions from the chat box.
हम लाइव होंगे ना, तब हमको बोले कि now we'll have a little message from our chief guest. तब मैं अपने chief guest है ना मिस्टर श्री प्रताप चंद्र सारंगी, उनकी वीडियो.
Mr. Edwards, there was some disturbance. Sorry for the disturbance. Mr. Edwards, can we have you online on the screen, sir?
Hello.
Yeah, he's trying to join in. Hello, sir. How are you doing? Can you hear us?
Yeah, I can hear you guys. Can you hear me?
Yeah, sure. Perfect.
Okay, perfect.
How are you doing, sir?
Very good, very good. How are you guys going?
Yeah, good, sir. Good, yeah. Excellent presentation, sir, I must say.
Thank you very much.
We have certain questions, sir. Do you want me to take the questions for you?
Yeah, sure. Start with whichever ones you want to start with. Yeah, I was just reading through them, but yep, go ahead.
Okay. Right. The first question is, sir, how you find out the material properties and which type of probes or sensors are used for this?
Okay, so yeah, so the material properties is really found out through the ROMAT PGS service. The ROMAT PGS sensor is what we call it, and in one of my slides I put it there. So we have actual coils within this sensor that detect material changes within the pipe, and we use this material change. We put it through a series of algorithms, and basically each particular material will give us a certain response, right? And we use this response or signal response to really determine the yield strength within that material. So that's really how these ROMAT PGS sensors work. There's a lot of algorithms behind in the background, but yes, that's exactly how it works.
Okay, sir. The next question that we have is, how can we enhance crack detection capability of a UT tool?
To be honest, crack detection is not my forte here. We do have a series of crack detection tools at ROSEN. So if you have some more specific questions on that, you can always shoot me an email. I can get you some information on these crack detection tools.
All right, sir. We'll go to the next question, sir.
Yep.
Can pig residue analysis data give us true material health indication of pipeline?
Pig residue analysis data. I'm not too sure if I understand that correctly. So you're talking about the residue, the sludge that comes out, and give us a true material health indication of the pipeline. To be honest, I'm not too sure with that question. we don't typically analyze the residue that comes out of the pipe. So yeah, sorry, I can't really answer that question.
All right, sir. We'll go to the next question. In pipelines, how can we generate pipeline DNA?
So pipeline DNA, this is what I talked about in my presentation. This is the name we call it at ROSEN, and it's really just about breaking down all the different material properties within the pipeline. So as I went through my presentation, the first thing is running this ROMAT PGS tool where we record the material properties and the yield strength, and we break down all the individual pipes into these buckets and populations, right? And so that really gives us this pipeline DNA. And then the next steps is obviously material verification, so going into the field verifying what the tool is telling us. And then it's gathering all your material testing records, it's all your records, and it's all the ILI data as well, and putting that all together. And at the end, that really spits out this pipeline DNA and really can give you an accurate representation of what's in your pipe. Yep.
Okay, we have one last question, sir. What is population in material verification of pipe?
Sorry, ask that question again. Sorry.
What is population? What is population in material verification of pipe?
Okay, so populations is the term that we define a particular group or batch of pipes. So one particular population may be a particular batch from a mill. It comes out from the mill with a certain yield strength distribution. It has a certain unique characteristics of diameter, wall thickness, toughness, and all these properties that define it as an individual population, right? It was made at a certain particular point in time. So that's really what we define as a population. And then we use these populations, right, to feed into our whole process. And what was the other second part of the question? There was population and then...
In material verification of a pipe.
Yeah, what is that? So yeah, so the first step is really defining these populations, right? If you want to call it, and then the properties of these populations, right? So you've got your wall thickness, you've got your yield strength, you've got your toughness. So the second step is material verification, is really verifying these properties of this population or these batch of pipes, if you want to call it, right? And so the ILI tool really gives us this first initial look at all these properties, and then we take a look into your records. And then the next step is the material verification, where you're looking at all your records, you're looking at your ILI data, and then you're going into the field and verifying that this is correct or this is not correct, and verifying the material properties of yield strength and toughness, and all these other stuff, as well as, we look at the microstructures of the pipe, really to get a feel for, the vintage and how the pipe was made. Looking at the chemistries of the pipe as well. So this is all material verification. Really, you're not just looking at your wall thickness and your yield strength. You go into more detail. You look at the type of pipe, where it comes from, which particular manufacturer, how it was made, and you're going really into the detail to really understand, the type of pipe that is within your system. And then this really feeds into all your FFP assessments at the end of the day. And when you have all this, quality information, then you can start to make these integrity decisions. When you start to see cracking on your line, when you start to have, corrosion related defects on your line, you really have a good understanding of these material properties within your pipeline, and you can start to make these decisions. So that's really, what we're trying to do with this whole, DNA process and material verification process. It's all about, knowledge, really, and the ability to make these informed integrity decisions with all this knowledge, and all these FFP assessments, build into it afterwards, right? And the foundation is really just this material verification.
Right, sir. Thank you so much for your time, sir. That's all from the KUHN session, sir. And we are really very happy to have you over here. Thank you for sparing time, sir. Thank you so much. And have a nice
No
day.
worries.
Yep.
Thank you, everyone.
Bye-bye.
Bye.
Take care.
Our next presentation is from LINSCAN, which is the student sponsor for Pincon. The presentation shall be done by Mr. ALFRED KUHN, who is CEO Europe at LINSCAN Advanced Pipeline and Tank Services. Mr. Kuhn is an electrical engineer with master's degree in project management. He is also a senior pipeline integrity advisor.
His area of specialization includes inline inspection, project management, PIMS, SCADA, and RTU. He shall be presenting his paper on advanced crack detection in oil and gas pipelines. Mr. Alfred Kuhn, please.
Hello and welcome to my presentation about advanced crack detection in liquid and gas pipelines. My name is Alfred Kuhn. I'm the CEO of the European entity of LINSCAN. I want to start my presentation with a safety moment, because safety is paramount for all that we do, and especially in the current situation of the pandemic, which is still raging on. So I want to remind you that you need to wear your masks properly, meaning they need to cover mouth and nose, avoid handshakes, practice social distancing, and practice good hygiene. Overall, don't let your guards down. Thank you very much for your attention to my safety moment. The agenda, I will go a little bit into basics. What is a crack? Why pipelines crack? Refer to stress corrosion cracking in more detail, and then I will introduce to you the options we have to detect cracks reliably. At the end, a brief summary of the presentation, some conclusions, and when we are ready for the discussion. First of all, we need to understand what is a crack, because this is an important part of the whole discussion about crack detection. And I'm referring here to the specifications as provided by the Pipeline Operators Forum, and which can be read in the version of 2016. A crack is a planar two-dimensional anomaly feature with a high length to width ratio, a sharp root radius, and a possible displacement, which means a surface opening of less than 0.1 millimeter of the fractured surface. A crack-like feature has a similar definition. However, the surface opening is between 0.1 and 1 millimeter. So this is the difference between crack and crack-like features. How does this look like in reality? You can see here schematic of a pipe wall and a crack, which is a disturbance in the metal grid, which does not necessarily have an opening. Whereas a crack-like feature has a distinct opening, and as it is written in the definition of 0.1 up to 1 millimeter. In reality, you can see here that this is what would be called a crack, and here this is a crack-like feature. This is important to remember, and I will come back to this a little bit later in my presentation. Why do pipelines crack? Pipelines crack because over time they deteriorate, and this deterioration or degradation increases over time. I've shown you here 4 examples of cracks which mostly occur across the globe, and this is fatigue cracking, hydrogen-induced cracking, sulfide stress cracking, and stress corrosion cracking. If you look at the abbreviations for C and D, this should not be mixed up. SSC is not to be mixed up with SCC. The first part we need to understand is, how does it come to cracking? And except for the fatigue cracking, which is that the material with repeated stress fatigues, gets brittle and breaks, The other types of cracking all require that there is a surface film breakdown. And the surface film breakdown means that there is a liquid between the coating of the pipe and the pipe wall. And this is where small pits start. And depending on the type of exposure of the pipeline to stress and the composure of the liquid, which is in that area where the barrier has cracked, it develops either into metal loss features or into cracks. Metal loss features are areas with distinctive metal loss, whereas cracks are characterized by a very, very small amount of metal loss, but a very big threat to the integrity of the pipeline. The characteristic of a crack is also that cracks grow over a certain period of time with a very, very small rate. But all of a sudden, and this is the danger of cracks, this rate increases dramatically and leads to unexpected failures. So the prediction of when cracks get dangerous is very, very difficult, and there is no reliable method developed so far which can determine when a crack will reach that exponential growth rate. This means that it is important to detect cracks early. The most dangerous and most occurring crack type is stress corrosion cracking, which goes back into the 1960s when the first types of this cracking were detected in the US, and which was later categorized as high pH stress corrosion cracking. The other type of stress corrosion cracking is near neutral pH, and this was first identified in Canada in 1985. What all these stress corrosion crack types have in common is that they appear in pipelines with high temperature, with high pressure, and also with alternating pressure. And this is not alternating 1 or 2 bars, this is high differences in pressure, 10, 20, 30 bar difference. And with many fluctuations of this pressure. We talk here about pressure cycling. Another characteristic is that this type of cracks appears very often in the first 15 to 20 kilometers after a compressor station or after a pump station. Now, how can we detect cracks? There are 2 technologies which are used for crack detection. In liquid lines, it's ultrasonic crack detection, or UTCD. And in gas pipelines, the electromagnetic acoustic transducer technology, also called EMAT. The difference between crack and crack-like features we have discussed already. Now, this is important to understand because this also gives us the explanation why tools based on the magnetic principle like MFL or TFI cannot detect cracks. They can detect crack-like features, but not cracks. And the reason is that in a crack, the magnetic field just passes along without being deflected. Whereas a crack-like feature deflects the magnetic field, and the sensors of the MFL or the TFI tool get a reading. So it is possible that the magnetic tools see crack-like features, but not cracks. This is an overview of feature detection capabilities. And the message here is that several tools exist for feature detection in pipelines, but there is no tool which can see it all. If we go back to the crack detection tools, I want to start with the oldest of these crack detection technologies, which is the ultrasonic crack detection, which is used in liquid pipelines. And the principle is that an ultrasound is generated, travels through to the pipe wall, and is reflected on the inner pipe wall and the outer pipe wall. And by the time which the ultrasound needs to travel back to the transducer, we can determine the distances. Now, if we look at the principle of wall thickness measurement, we see that the sensor is in a 90-degree angle to the pipe wall. And this means that if we have cracks in a pipeline, our ultrasound, because it is in a 90-degree angle, will not see these cracks. So the data analyst later on, when he sees the data from the tool, he will see nothing in the data. So this is why the crack detection tool was developed. And the principle here is that the sensor is not at a 90-degree angle to the pipe wall, but at a 17-degree angle, which means that the ultrasound beam, when it is entering into the pipe wall, is traveling in a 45-degree angle, and that cracks in the pipe wall will reflect the part of the ultrasound, which can be read by the transducer. This happens from both sides, so that we get a reading from the left side or from the clockwise side or the right side, which is also called the counterclockwise side of the crack detection tool. So every crack will be seen from several sensors and from both sides. And by this arrangement of sensors around the circumference, we achieve a high probability of detection and a high probability of identification and sizing of crack features. The tools which exist on the market generally can all see longitudinal cracks. There are certain companies who also offer the detection and identification of circumferential cracks. The report that you receive after a crack detection inspection is the same format as you know it from metal loss inspections, the feature list with all the features which have been found with their dimensions, locations. You get also the distribution plots along the pipeline. The difference is that compared to a metal loss inspection severity assessment, which is giving you an estimated repair factor, the crack detection assessment gives you an anomaly assessment factor, and the repair curve looks different. These are some examples of real cracks which have been found in real pipelines, longitudinal cracks, and also axial cracks. The other tool which is used for crack detection is the EMAT. And this tool was especially developed for the use in gas pipelines. Because in gas pipelines, the standard UTCD tool cannot be used because there is no liquid couplant. And no gas pipeline operator wants to have a liquid couplant in his pipelines, because this requires afterwards cleaning, drying, which is cost intensive. So the EMAT tool was developed, and you can see the difference between the two methodologies. The UTCD tool needs the liquid couplants to transport the ultrasound from the transducer into the pipe wall. The EMAT tool uses also an ultrasound. However, the ultrasound is created inside the pipe wall. The picture shows the difference between the standard UTCD tool and the EMAT tool. The ultrasonic crack detection tool uses a liquid couplant to transport the ultrasound which is created in the transducer into the pipe wall. The IMATS tool, however, creates the ultrasound inside the pipe wall. The picture shows the two different methodologies that the tools use. The ultrasound crack detection tool uses a transducer, and the ultrasound is transported from the transducer through the liquid couplant into the pipe wall. The IMAT tool, however, creates the ultrasound inside the pipe wall by a fluctuating magnetic field with a high frequency, which makes the metal grid swing and creates the ultrasound inside the pipe wall. This is how the IMATS tool looks like. It is a little bit similar to the magnetic flux leakage tool, which you may know. And this is because it uses a static magnetic field and also a fluctuating magnetic field to create the ultrasound inside the pipe wall. The benefit is that you do not need a liquid couplant, and an additional benefit is that this tool may also see coating disbondment. Here you see the two principles of creating the ultrasound in the pipe wall. One is using Lorentz force, the other is using magnetostriction, where my company has opted for the magnetostriction method, which gives certain advantages over the Lorentz force method. The biggest advantage is that the sensors do not need to be that close to the pipe wall as with the Lorentz force method, and that we get a better level to noise ratio for the reflections which come from the features inside the pipe wall. Here are some findings of the IMATS tool. We have a crack field, we have a gouge, and we have here an area of coating disbondment. The coating disbondment is determined by a difference in amplitudes, because where we have the coating attached to the pipe wall, the resulting amplitude is lower than from an area where we have no coating directly at the pipe wall. And if we have an area of approximately 60 square centimeters, then we can determine that this is an area of coating disbondment. It must be said that this must be a full area where the coating is disbonded from the pipe wall. To come to the end, efficient crack detection is available for liquid lines and for gas lines. In liquids, it is the ultrasonic crack detection tool. In gas, it is the IMATS tool. Both methods have a high accuracy in detecting and sizing cracks and also crack-like features. One recommendation at the end: every crack detection inspection should be accompanied with an inspection for metal loss. The reason is that some metal loss features may have a sharp edge, and this sharp edge may be interpreted as a crack. So by the combination of the crack detection and the metal loss inspection, the data analyst has it much easier to determine what kind of feature he is looking at. So therefore, the recommendation to have a metal loss inspection accompanying every crack detection inspection. Thank you very much for your attention, and now I'm ready to take your questions.
भाई वो प्राइवेट प्रॉपर्टी है उसकी
मस्का बन खा लो
Can you hear us?
I can hear you.
Hello, sir. How are you doing?
I'm not too bad. Thank you very much. Good morning to India.
Good morning, sir. That was an excellent presentation, sir. And we have received certain questions, sir. Or do you want me to take them for you?
Yes, please.
Okay. Right. The first question for you, sir, is how does crack lead to failure?
Well, it is a similar process than with metal loss features. The pipe wall is losing its strength. The metalcrete is disturbed, and by the crack growing, this disturbance poses a bigger and bigger threat to the integrity of the pipe wall. And at some stage, the pipe wall just breaks open.
Okay. The next question for you, sir, is what's the difference between fatigue cracking and stress corrosion cracking?
There are two different processes. Fatigue cracking happens when we have pressure oscillating many times. We call it pressure cycles. And you can create fatigue cracking yourself when you are bending a piece of metal many times. You will see that it becomes brittle in the middle, and you will also feel the heat when you move it many times, and at some stage it will crack. This is fatigue cracking, where SCC needs heat, needs a liquid, and is also susceptible to pressure fluctuations. So it's different processes.
Okay. The next question, sir, we have over here is MFL tools cannot actually check crack inspection, or it can check only crack-like inspection.
This is correct. As I explained, this is a physical point, and this is explained by the definition of what is a crack and what is a crack-like feature, because the magnetic field just travels through the metal grid, even if there is a disturbance in the metal grid, which is the start of a crack developing. And as the magnetic field can just travel through that area, there is no deflection of the magnetic field, and the sensors of the tool get no reading.
Okay. The next question is, sir, how do the nature or type of cracks differ between pipes going underground and pipes under water bodies?
There is no difference. The important point is the process, which happens, meaning how is the pipeline operated, how is the coating condition.
Okay. The next question is thermal fatigue a significant mechanism for failures of pipes in oil and gas industries?
It is, well, it happens, but this is not the most occurring failure mechanism. The most happening and most severe mechanism is SCC, and then followed by fatigue cracking.
Okay. The next question is, sir, can UTCD tool detect coating disbondment in liquid pipelines?
No. That would be nice to have, but this is not possible.
Yeah. We have one more question, sir. Any complete case studies that you can share?
Many. I mean, we have completed many crack inspections, and over my business career, I have worked on maybe 100 to 120 pipelines where we did crack inspection. So there are many case studies to be shared. Yes.
Okay. Another question that we have is which technique is useful for detection of lamination defects?
Ultrasonic wall measurement, the standard ultrasonic tool. This is the one to use if you want to find laminations, mid-wall laminations, especially.
Okay. And which exclusive technique is used for detection of circumference crack?
This is the crack detection tool with a different orientation of the sensors. I mean, we in the standard configuration, the tool detects longitudinal cracks. And if we rotate the sensors by 90 degrees, we can detect circumferential cracks. And with our tool, this can be done in the field. So the sensor orientation, within 1 day, the tool can be converted and can be run to detect circumferential cracks.
Right, sir. Thank you so much, sir. That is all we have in the Q&A session. It was really nice to have a chat with you, sir. Have a good day, sir. Thank you.
Likewise. Thank you very much.
Bye-bye, sir.
Bye-bye.
Moving on, our next speaker is Mr. BIDYUT BANIAH, who is currently with Allied Engineers as Chief Project Manager. Mr. BANIAH is a specialist in ECDA, ICDA, SCCDA, pipeline integrity management and assessment. He's a chartered engineer in metallurgical and materials engineering and has a bachelor in petroleum engineering. He is also a member of Institution of Engineers India, ASME and NACE International.
He is going to present the paper titled Utilization of High Resolution Integrated Indirect Inspection Survey Technologies as part of the DA methodology of aging non-CP pipeline network. Mr. BANIAH, please.
Hello, good afternoon, everybody. This is the first ever Pincon, that is the Pipeline Integrity Conference. Welcome, everybody. I'll be talking about the subject called Utilization of High Resolution Integrated Indirect Inspection Survey Technologies as part of the direct assessment methodology of aging non-CP protected pipeline network. We're going to be talking about pipelines which are not cathodically protected, and these are upstream pipeline that we'll be talking about. I'm going forward now. That's my introduction. I'm directly going into the subject of this presentation, which is talking about the network of the client, which includes a rich gas pipeline network of around 31 pipelines, 185 kilometers, lean gas pipeline network, 3 pipelines, around 37 kilometers, and gas lift pipelines, 8 numbers of around 94 kilometers, and of course, crude oil delivery pipelines. In total, there were total 50 pipelines or so of more than 400 plus kilometers. None of them are CP protected, but they were designed to be so. So it's not, they were intentionally not to be put in categories is that the CP system not working. It was designed not to be CP protected, so it's okay. And these are upstream pipelines, and these are also designed on a temporary basis. And these pipelines are pretty old. Some of them go back to 1975, which is almost 45 years old, to even recent pipelines, which in some sections in some pipelines have also been replaced, which could be replaced in last 2018 or something that we have records of. The kind of pipeline that we're talking about is it's an upstream pipeline network. It's temporary pipeline systems, as already mentioned before. They are all non-CP protected, and it's highly clustered. Of course, we'll show some photographs so that you get an idea of what kind of pipeline we're talking about in this particular case. But what the client needed in this case was they needed a technology that could be used to isolate and map these kind of pipelines, which is the key and key subject of this presentation, and we're going forward based on that. Some live examples of such pipeline network is some photographs that we're talking about here. All the pipelines are together. Some of them does not have coating, some of them does have coating. They are all going together like this on bridges like this. Some of them are bigger diameters, some of them are smaller diameters, some of them are touching each other. They're all steel pipelines, mind you. So each steel pipeline touching each other, it means that they are all electrically continuous. One more example of this. Sometimes the pipeline comes above ground on its own and then goes underground again. Something like this that we're seeing over here. It's because the soil in that area have subsided, or maybe just general erosion of the soil has occurred due to a lot of precipitation in the area. Again, some examples like this, and some of them are also, it could be such a case that one pipeline within that whole bunch was laid maybe 2 years ago, and another pipeline was laid maybe 30 years ago. So that could also be the case in this area. Another photograph of our guys doing the survey. What are the key properties of these lines? Minimal coating left. It was not designed to be CP protected, and because they are all together and touching each other, and there is no insulation joints at the stations, they are all electrically continuous. And to actually assess the integrity of such pipelines, whoever the contractor is, or anybody in the future as well, they need to have a tool that can actually isolate these pipelines from each other. So each of these pipelines can be identified, so we can assess them accordingly. What are different surveys used during this indirect inspection survey? During this process is what we have to do is we'll be using a technology called XLI in this particular case, in this particular project. That's how we do the survey, with two guys side by side, parallel to each other. One guy has a line locator and on the GPS backpack, and the other guy has the probe for recording all the readings. And these are all the items that are being collected at the same time in this particular case. So we have to be collecting all of them to ensure we have enough data to assess integrity after end of this program. So we are collecting GPS, we're collecting continuous depth of cover, which is also very important for ICDA programs. We're collecting native SIPs. It's not normal SIPs. Normal SIPs would have been in the case of CP protected pipelines. But in this case, we are collecting what the native potential is of the pipeline. That is what kind of potential is the line seeing from the environment as it is without any in place impressed current cathodic protection or a sacrificial anode cathodic protection system. We're not doing any DC kind of a survey. We're not doing DCVG. So we're doing ACCA in place of that, as well as ACVG. The survey, after we complete the survey, this is how it looks on the software. And these are the different data sets that we collect on the same time, and it's aligned automatically. So we get native SEPs, we get the CAT data, we get the ACVG data, we get the elevation data, we get the depth of cover continuously data, and of course the plan view with all the lat longs and everything. What that does is, after you finish a survey like this for many of these pipelines, which we have done in this particular case, imagine the kind of pipeline we just saw a couple of slides ago, when all of them are touching and all of them are crisscrossing each other. Finally, you get to a point where we can isolate and have them map like this. This is an operator's dream come true for such a case. I mean, having this done for non-CP protected pipelines, that too in a situation where all the pipelines are touching each other and all together. So this is quite a unique feature and something that takes a lot of time and effort, but it can be done if the right technology is deployed. So we'll be talking about the results of this kind of a survey that was deployed for this kind of a program. So therefore, we'll be talking right now of the readings as well as what was actually found during the inspection, the verification inspection process. So this is one location at 221 meters. We have high attenuation and a peak ACVG fault as shown there. And this is how we see it in the field. We see a coating holiday, another coating holiday, and underneath the coating holiday, we are seeing a lot of external corrosion, pitting external corrosion. So we are actually finding out corrosion from these kind of surveys. So that's, I mean, if you see from the NACE perspective of the NACE ECD standards, any of these above ground survey technologies, they are not directly, or they are not supposed to be finding you external corrosion. They are supposed to be finding you indications. What is an indication? As per NACE, an indication is anything out of the norm, which is picked up and which is electromagnetic in nature, and it's picked up by the above ground survey that was done earlier. But in this case, we are pretty lucky. We found holidays and we found associated external corrosion along with the holidays, and we could categorize them accordingly. So which is quite a successful process during this project. Another example is we see an indication which has been ACVG flagged. This is quite startling even for us, even though we've been using this technology for quite a while now. We find a welded plate which had previously must have been a repair in this area. If you can see where my mouse is, another holiday and long holiday. And additionally, we are also finding a leak. This was a live leak. After we removed the coating in that particular site, we actually find a leak, and we had tested this with bubbles to see that the leak was incoming. I mean outgoing. Sorry, it was outgoing in that particular case. So we actually stopped a catastrophe in that area because we find a leak by using indirect inspection technology. That is quite something, because again, I would like to reiterate, we are not supposed to be finding leaks through doing indirect inspection technologies. DA as a technology is meant for finding metal loss. It is not meant for finding leaks. But sometimes the data connects and it does make sense. The science makes sense, and we end up picking up the right location for finding leaks like this. In another location, we find we have caught an indication which was flagged as a coating anomaly by ACVG. But of course, when you do the excavation, then we see that it was not exactly a coating anomaly. It was a coal tar coated pipeline, and the clamp on which there was a leak before. It was the client had repaired the leak using a clamp, and the clamp was left bare. Therefore, our technology, the machine that we had deployed, it saw that particular clamp, the bare clamp, as an indication which got flagged during our data assessment, and therefore could catch it. And this is again something quite amazing, because even for us, as we have been doing this kind of surveys, and it's difficult to see something like this by using indirect inspection technologies. This is another example. We see a coating holiday. What we're trying to show is, you see a holiday like this, and you open up the coating, and then you see that the coating is moving away from the pipe, which is known as disbonding. So the coating is moving away because of disbondment, and you know why it is disbonding. It's because based on the holiday, the area started corroding. So the deposits have created the coating to be disbonded off from the pipe, so that the coating is just sitting on the pipe, but it's not exactly adhered to the pipe. This is another example where we're talking about, okay, this is another case. So in these old pipeline systems that I'm talking about here, where some of the pipelines are more than 45 years old, some sections, because of previous historical problems, some sections were replaced. And now that the industry has moved on to 3LP type coating, those replaced section was 3LP coating. Even though the pipe material is the same, but the coating is different. The original coating was coal tar, but now the replaced section has been 3LP. But even in this area, we could still see holidays, and something like this was caught. And if you see the attenuation in the area, it's less compared to the coal tar attenuation that we saw earlier, couple of slides before this. So this makes sense because this makes scientific sense as well, because the 3LP coating is in place exactly. It's not degrading like the coal tar coating is. Plus we know it's new coating, therefore it's not supposed to be losing out on attenuation. But still there was a holiday which was most probably caused by a third party defect or something, and which was caught by the program. And we had removed it and also checked for disbondment, which we found a little bit of disbondment, even though this replaced section was only 2 years old. This is another example that we're talking about. In this case, it's moderate DOC. Depth of cover is less, which is what it means. Minor ACVG and no attenuation. So what in this case we're trying to show to the audience here is we're trying to show whether this program will also work for a location where there is no indication to prove the kind of a null site per se, where because we have to also show that if the technology is not catching something, does it mean we are missing something? No. So just to prove that we've got this slide in, and this is what we're going to talk about here. So this was in particular a null site, and after excavation, that is what we find. We find perfect coating in the area. There was one pipeline crossing on top of it, and we see that the subject pipeline which was being surveyed, that pipeline did not have any coating anomalies, nor does it have any problems. Although the pipeline on top, which the one which is crossing, those had a couple of coating holidays, and most probably the ACVG minor indication that we got in this location could have probably come from this pipeline which is crossing over our subject pipeline in this particular case. So this was quite impressive, and with this I come to an end that when you do such niche old pipeline system, and when your pipeline system is critical to be assessed, you might require for additional indirect inspection technologies. You cannot just hope that two will do it for me or one will do it for me. You'll have to go for maximum resolution, which is the subject of this presentation, and that's how I close this topic for the day. Thank you, and please let me know if you have any questions.
Thank you, Mr. BANIAH, for the presentation. Can we have you on the screen, sir?
Hi, good morning, everybody. I am available. Can you listen to me?
Yeah, we can hear you perfectly fine, sir. How are you doing, sir?
All good, thank you so much.
So it was a very nice, informative presentation with so many case studies. We really enjoyed it, sir.
Thank you.
We have received certain questions in the chat box, sir. Would you like me to take them for you?
Please.
Okay, sir. The first question is, how does indirect inspection differ for non-CP pipeline from CP pipelines?
Yes, at the outset, I would just like to reiterate here that I have a team of CP engineers. I'm the project manager for this. So if I may not be able to answer all your questions, please bear with me. I will get the answers to you. So if you can send those questions, I'll try to answer your questions right now. But if I cannot, in that case, we'll get back to you. So please bear with me on that.
Sure, sir.
Yeah, so can you repeat the question, please?
Yeah. How does indirect inspection differ for non-CP pipeline and CP pipelines?
Well, it's not the tools are same. It's just the methodology, how you customize it for that program. In this particular case, the methodology that we had adopted, we had to do a lot of preparation prior to even starting the survey itself. So which required us to do a lot of intermittent digs, a lot of excavations, a lot of small well excavations to check if we're okay or not, to connect the pipeline, connect our transmitter directly onto the pipeline. So we did a lot of exercise, maybe 1.5 months of exercise before even starting the survey. So we had to do a lot of customization in this case. So by doing all those exercises, we could make a customized program which actually worked. And it did involve a lot of civil work, which is a lot of excavations. It does get difficult for all these things to happen, but when you need to do something, some assessment of these kind of pipelines, you need to do some work, which in the end gave the results that the operator was looking for. So it worked all out.
Do we have you, sir, with us?
Yeah, I'm still here.
Yeah, that's fine. The next question is, sir, can CAT or ACVG survey identify location of a coating defect?
Absolutely. I mean, ACVG is a not exactly same, but it is similar in nature to DCVG in trying to pinpoint a coating anomaly. But CAT is more of a subjective and qualitative basis technology, which gives an overall area of pipeline if the coating is degrading or not, and if it's losing out current because of the degradation. So ACVG helps pinpoint an anomaly. CAT will give you a generic location that this area is not good. CAT does not help in pinpointing.
Okay, sir. The next question is, why DCVG surveys was not considered in the deployed tools? Any specific reason?
Great question. Thank you, sir. I mean, we tried DCVG. Because these were not CP protected, we deployed temporary transformer rectifiers. We deployed temporary battery sources, current sources, and then we started doing these. We started injecting current to the pipeline. But because, like you have seen in the slides, the pipeline, they're all touching each other. So as soon as any first contact happens, the DCVG current is lost, and it goes to all the other pipelines in the network because they're all electrically continuous, like we said. Therefore, DCVG could not be applied. And even if you wanted to increase, switch on, turn on the current a little bit more, what happens with that is then it's a safety threat to the pipeline system because we don't even have an IJ. So that current could flow back to the installation, the plant, and create a HEC incident, which we do not want.
Right, sir. The next question that we have is, how could you do native CIPL on a non-CP line?
Great question, sir. Yes, we could do it because of this particular instrument that we had used. The survey that we do in our pipeline, we had used the transmitter that injects AC current at 1000 hertz, which is quite high compared to any other transmitters in the market. Therefore, that allowed us to get 200, 300 meters of survey time per pipeline. So like I said earlier in the first question, we had to do digs again. So maybe we are doing a dig in the first 0 meter, or we're connecting the pipeline directly to the pipeline, and then we dig again another 400, 500 meters downstream to connect our transmitter directly onto our pipeline. So lot of permutation combination in terms of excavation and connecting the transmitter directly on the pipeline and seeing if we are on the correct pipeline or not. That helped.
Okay. We have another question, sir, from Mr. B. Pawan. How the particular pipeline will be located if electrical continuity is existing in those bunch of non-CP pipelines?
Absolutely. This is the same question, same answer to what I just said. We have to, I mean, we are using this 1000 hertz AC current injecting transmitter, which helped. And that was the unique part of this job. How when you deploy something like that, that helps do this. But even when it helps, it does only help us for 200, 300 meters. So we have to dig again. But it does make the process intensive and, more, it takes a lot of time. But when one has to do it, you have to do it,
One last question, sir. Does this survey work in paver block area or cement concrete road?
Great question. Just to give you and quote NACE International on this, none of the indirect inspection techniques with the principles involved currently can do inspection on cement concrete road or in paved block area. Sometimes ACCA or CAT will be working, but again, it's very qualitative. It's not quantitative. So you're going on your luck over there. As long as you get depth of cover and GPS for that section, that should be good enough. But yes, ACVG, DCVG, and ACCA will not work. SIPs will not work in this area.
Okay. We have one last question, sir. This is, can CAT ACVG in a congested pipelines corridor be done as pipelines may be touching each other and signal may travel to each other?
Yes, that's what we did. I mean, I think I answered this question already. ACV, we had to use we had to bank and depend on ACVG primarily to find out coating anomalies for these lines, and this was done using our 1000 hertz ACVG AC current injector.
All right, sir. That is all in the Q&A session, sir. Thank you so much, sir. You have been very considerate to answer all the questions that were posed to you.
No, thanks a lot. Thanks a lot, guys. Thanks a lot.
Bye-bye, sir. Take care. Have a great day.
Our next speaker is Lieutenant Santosh Kumar, who is specialized in integrity management of cross-country pipelines and storage. He is a metallurgical engineer from NIT Jamshedpur and is currently Senior Manager Inspection with Indian Oil Corporation Limited.
In addition to his services, he has served 3 years with the Indian Territorial Army. He is going to present a case study on role of fatigue in safe operation of pipelines. Mr. Santosh, please.
Hello everyone. Welcome to the session chair, the organizers and the speakers and the delegates. Today I will be presenting a case study on topic of role of fatigue in safe operation of a pipeline. Thanking you, the session chair, for introducing.
How can you do native CIPL?
Fine, sir.
That one, like you went to the AC way, we are connecting transmitters, but CIPL तो मतलब BC के लिए होता है.
Introducing me to this conference. In this case study, the pipeline which we will be discussing, it is a pipeline which was laid in 1996 as a 1330 kilometer long multi-product pipeline. Flow rate ranged between 750 to 900 kiloliters per hour. This is the schematic of the pipeline. So nearly after 10 years of service in 2006, this pipeline was changed to crude oil service, primarily high sulfur crude oil, and its length was reduced to 1174 kilometer. And this is the schematic of the pipeline after change in service. So due to this change in service requirement, several pump stations were also added in between to meet the flow requirement of the refinery crude oil. So as of now, there are total 9 pipeline sections in this pipeline. So as a background, axial MFL based inline inspection was carried out for this pipeline in 2012-13. And based on the report, all the critical and subcritical defects were repaired. And also it was seen that in none of the pipeline sections there were any serious nature of corrosion defects. And the defect sentencing curve from one of the section is evidence showing that the defects were not so critical in nature. Thereafter, in between January 2014 to December 2016, there were 5 pipeline ruptures in section 2, 7 and 9 due to opening of longitudinal double submerged arc welded seam, and 1 leak in section 9 from longitudinal weld seam area. So there were total 3 failures in section 9, 2 in section 7, and 1 failure in section 2. This schematic below showing the position of the failures in the pipeline section, and these are some of the photographs of the failed pipe. So we can see that the pipe has opened from the long seam area. So as a further action to arrest the possibility of any similar scenario in future, a detailed study was needed to be taken up covering the following aspects: review of all features, all failures to assess their commonalities, like what was common between all the 6 failures, then what was the role of pressure cycling index in the failure, the role of search and change of service in failures, and evaluation of remaining flaw size, which was equal to the detection limit of INLINE tool. So this presentation will primarily discuss the role of pressure cycling, surge, and likely effect of change in service in these failures. Also, a few probable remedial measures to counter these failures have also been highlighted in the end of the presentation. So when all the pipeline failure reports were reviewed, upon comprehensive review and detailed study, it was seen that primary contributors of all these pipeline failures were as below, and they have been ranked as per the given serial number. The first one being the weld flaws at the internal weld of the pipe, and the second one was fatigue growth of the initial manufacturing weld flaws, which over the years would have grown and led to the failure of pipeline. And also this pipeline was vulnerable to surge, that is exposure to pressure which was exceeding 110% of the MAOP. And potential of hydrogen damage was also prominent due to change of pipeline service and other environmental growth mechanism might affecting the corrosion as well. However, there was no real contribution of corrosion in any of the failures. So upon the review of fatigue growth of weld flaws, it was seen that weld flaws like weld misalignment, weld undercut, or lack of fusion at the toe of internal weld were appearing at near point of fracture initiation. So one of the first failure photograph showing from the scanning electron microscope is showing that fracture initiation zone of the sample and the brittle facets at the inner edge, midsection, as well as the outer edge of the pipe. And then repair of the original longitudinal weld also led to the increase of hardness of the pipe weld, and hence the weld got more brittle, which would have further contributed to the failure of welds. Also, contribution of corrosion was not evident in any of the failures. The third and fourth photograph shows the initiation of a small crack at the toe of weld, and the fourth one shows the weld misalignment of the longitudinal seam. Further, fatigue growth of weld flaws were also reviewed. So it was seen that cyclic index values were calculated for all the sections using rain flow counting method as per ASTM E1049, and pressure data was used for the period when the line was operating at the current operating pressure. So it was seen that section 9 was having aggressive cycling index, followed by section 5, 3, 2, and 8. And all these pipeline segments were getting aggressively cycled. So these fatigue led to the further incremental propagation of the crack defects, and this leading to the failure of the pipeline. And these photographs shows how the fatigue crack has initiated in the weld cavity. And the second photograph on the right is showing the nucleation of number of micro cracks from the pre-existing lack of fusion. And for controlling the effects of fatigue, following actions have very significant potential, which can reduce the cycling index in the pipeline. That is number and intensity of pressure cycles. The first one being the reducing number of shutdowns, that is minimizing pump start and stops. Then holding back pressure. This will obviously be subject to the operational requirements if such holding back pressure is feasible or not. Using friction reducing additives like DRA, and modifying product batching and delivery and receipt schedule so that there are very less number of shutdowns due to unavailability of the storage tanks, etc. So as I indicated earlier, that currently the pipeline is operating at quite a low operating pressure, that is 60% of SMYS, as compared to its design of 72% of SMYS. So vulnerability of surge was also reviewed. It was as shown earlier. It is seen that except section 2 with the last failure, all the sections are exposed to surge conditions, and the surge potential is in excess of 110% of the pipeline design pressure. So all the observed failures, it was seen that all the observed failures correspond to a potential surge event during the operation time, and this might have led to an increased risk of failure in all those cases. And it is also seen that failure occurred even at lower stress level when the MOP of line was far lower than the current MOP. So this is likely due to the combined effect of fatigue growth of defects added with the surge event in some of the cases. So for controlling the effect of surge, following actions can be taken. Surge relief systems can be installed in all sections where closure of one or more valves can result in surge pressure exceeding 110% of the design pressure. And based on the surge analysis carried out for this pipeline, such surge events is expected to be more in section 4, 6, 7, 8, and 9. So these are the sections where surge relief systems need to be installed. And thereafter, remaining life of crack-like defects and weld flaws were also evaluated. So it was seen that remaining life of all the detected flaws in the INLINE run. Yes, we carried out UT crack detection INLINE of this pipeline in around 2015. So there were some defects which were reported. So remaining life of these detected flaws were found between 0 to 12 years. But however, all these flaws were already repaired immediately after having the INLINE report in hand. So this 0 to 12 year re-inspection criteria is re-inspection requirement is no more there. And the least value of the remaining life of crack-like anomalies, which was taken as equal to detection threshold of the INLINE tool. It was assumed that there might be some defects in the pipeline which would be equal to size of INLINE detection threshold, which was 30 mm long crack and 2 mm depth. So upon its assessment, it was seen that in the current operating condition, it would survive at least 63.2 years. So this was calculated based on the current operating condition and the MOP associated with 65 and 72% SMYS. So this implies that detection threshold of INLINE tool was optimum for detecting the defects in the pipeline. Thereafter, the change of service and hydrogen damage was also reviewed, and it is seen that this pipeline was converted to crude oil service in 2006, and due to change in crude oil service, it would have created an operating environment which contains more hydrogen in the pipeline, and this increases the risk of hydrogen damage being present. The result of hydrogen damage susceptibility study was done through a consultant, and they suggested that chances of the hydrogen-induced cracking or sulfide stress cracking is a likely factor in all these failures. However, this study did not evaluate the effect of repair weld, repair of pipe long seam welds, and their effect on microstructures and weld flaws such as lack of fusion, undercut, etc., which would have led to more susceptibility of seam welded X65 grade pipe to hydrogen-induced cracking. And this is likely to get affected by the hydrogen environment in the pipeline. After this, what action was taken, as I previously told, that UT crack detection INLINE tool was used in the pipeline in 2015, and all the reported defects, mostly from section 5 to 9, they were repaired, and the least value of remaining life of INLINE defect with size of detection threshold of INLINE tool, it was 62.2 years, as already covered in the previous slide. And after this, 72-kilometer pipe replacement was also done, and further pipe is now operating at quite a lower stress level of 60% of SMYS, though the pipeline was designed to operate at 72%. And also the DR injection is being done in this pipeline to gain the throughput of the pipeline at a lower operating pressure. This is further reducing the effect of pressure cycling as well. So what the challenges we are having? So the INLINE tool was unable to identify cracks, and rupture took place in the pipeline even after INLINE was done. In this case, UT Sharewave 45-degree tool was used with a sensor oriented at 45 degree. So orientation of cracks would have prevented this tool from detecting these anomalies. And the INLINE agency concluded that the geometry of anomalies going within the pipe wall represents one limitation of the technology for the proper depth calculation. The graph below shows how the position of defect can affect its detection capability by an INLINE tool. So orientation of defect at a particular angle prevents INLINE tool from detecting that defect. Further, after the seam rupture in January 2014 in Section 9 and March 2015 in Section 7, operating pressure was reduced by 20%. But even then, one rupture took place in both the sections again. So this indicates that well defects continue to grow at even lower operating pressure as well. So challenge is to identify such defects and repair them before they fail. And further, as a way forward, these are the steps which can be taken to avoid similar failure in the pipeline. So introduction of such leaf system can be done at all those places where the pressure is in excess of 110% of the pipeline design pressure. Injection of DRA to reduce pressure cycle amplitude can be done. This will also help in achieving the required flow rate at a lower operating pressure. Monitoring of pressure cycle of all the pipeline sections should be done so that we are aware of what kind of pressure cycling is taking place in the pipeline sections, and if required, any remedial measures can be taken accordingly before it leads to similar kind of failures. Sections with higher pressure cycling can have manual operation, which is quite likely to reduce cycling as compared to automatic auto operation. And scheduling of the crude oil batches shall be done in such a way that there is a minimum shutdown in the pipeline. Like sometimes scheduling, improper scheduling might lead to shutdown of a pipeline due to unavailability of tanks. So scheduling shall be done in such a way that there is a minimum shutdown in the pipeline. Also, holding back pressure can lead to decrease in amplitude of the pressure cycle. However, such changes are not quite easy and it is subject to the operational requirement, and also a detailed analysis and study might be needed to go on this way. Also, future crack detection INLINE inspection by using most advanced high resolution ultrasonic shear wave technology can be done using multiple angle probes like 45 and 30 degree. Like in present case, we had used only 45 degree. So at least two angles can be used so that a defect chances of detection of a defect is quite high. Or emerging technologies like EMAT can be used. And reassessment of INLINE data through a third-party agency can be done so that none of the defects are missed during the data analysis. So that's all from my side. Thank you all, and I open this session for any discussion. Thank you.
Thank you, Mr. Santosh, for your presentation. Can you hear us, Santosh sir?
Yeah, his video is loading. Mr. Santosh, are you with us?
Let's give him a few seconds.
Yeah, he's trying to join in. I think his audio is already joined. I would also like to request our technical team in the back end to please keep their mics on mute, please.
Sir, can you hear us?
I think he's trying to rejoin. That was a very informative session, no?
Yeah, I hope all our viewers are finding all these presentations fruitful and engaging. Sir, can you hear us?
Yes, I can hear you loud and clear.
Good morning, sir.
Good morning.
How are you?
Fine. Thank you.
Thank you, sir, for your presentation.
Thank you.
Okay, we've got some questions. What are the controlling measures to reduce risk of surge events?
Like as I covered in my presentation, 2-3 things can be done to control effects of surge. One is that first and foremost, if a surge analysis needs to be done for a pipeline, and then if any of the section is having surge pressure in excess of 110% of the design pressure, so we need to install a surge relief system for those sections. So that would be a basic requirement in for controlling surge in a pipeline.
Okay. Why change?
And one more thing, in some cases we have been seeing that manual operation does help in controlling sudden pressure variations in the pipeline. So that may also help to a certain extent.
Okay, sir.
Yes.
Why change of service of pipeline is major cause of pipeline failure?
Like as I covered in my presentation, this pipeline was initially laid as a product pipeline. So after change of service, this is primarily transporting a high sulfur crude oil. So this high sulfur crude oil is creating a hydrogen-induced hydrogen environment in the pipeline, primarily due to hydrogen sulfide in the pipeline. So that can lead to like hydrogen-induced cracking or sulfide corrosion cracking in the pipeline. Though as of now, in the present case, we did not find any such effect in the pipeline, but then it can contribute definitely in certain cases.
Okay. Any microbiological analysis is done in some of the failure analysis?
Microbial analysis we normally indeed do for our pipelines whenever during the pigging mark is received. The microbial analysis is indeed carried out. In the pipeline failure cases, there was no enough, like you can say, the substance available in the cracked portion of the pipe wherein we could have carried out the microbial analysis. And as we know that any microbial analysis needs to be done, like the samples needs to be collected as soon as possible, and they need to be collected and stored at a suitable temperature so that the species of the microbes are saved and its assessment could be done. So in this case, it was not done, but then we had the backup data from the picking of the pipeline, if the line is suffering from microbial analysis or not. So in present case, it was not there.
Okay. We've got one more question. What are the major challenge in failure of pipeline?
Major challenge in failure of pipeline, like what I understand from this question is that like the person who has asked, does he mean to challenge after the failure of pipeline? If that is the question, the primary challenge is that damage to the environment and areas nearby. So it is affecting the public and the environment. So that is the major challenge.
Okay. What are the learnings in the case related to rupture of pipeline?
In the present case, the primary learning was that the two things we learned, like it was the pipeline was suffering from inherent weld defects, and that need to be controlled. The growth of these defects cannot be overruled, so it will continue to grow. The only thing we could have done is that its growth can be rate of growth can be reduced to a certain extent, which we are doing by reducing the operating pressure of the pipeline. We have restricted the operating pressure. We are not going beyond 60% of SMYS, though pipeline is designed for 72% of SMYS, and we are also using DRA to gain the throughput of this pipe with a lower operating pressure. So these were the main learnings from this pipeline, and the change of service, the way which it impacted the happening of these ruptures.
Okay. Thank you so much, sir.
Thank you.
For answering all the questions. Thank you, sir.
Thank you so much.
And now it's time for a short 15 minutes corrosion podcast break.
We also have video messages from Executive Director HR IOCL and Executive Director Construction IOCL for the conference. Let's have a look.
We shall be starting with Symposia on Marine Corrosion thereafter. Stay tuned.
Welcome to Corrosion Podcast Part 2. This course shall take 5 minutes only. Enjoy the science behind corrosion.
Good morning, Mother.
Good morning, beta. Ready for school?
Yes, Mother. Late हो गया हूँ. Bye, Mom. See you after the school.
Bye, beta.
Good morning, teacher.
Good morning. Please sit. Today, we will talk about examples of corrosion. And I hope any of you might have visited some monuments so far.
Oh yes, ma'am. कल मैं अपने फादर के साथ कुतुब मीनार गया और मैंने वहाँ आयरन पिलर देखा.
Great, Rahul. That's a wonderful example of rust-free monument in India. Now let me tell you about critically designed buildings which got badly corroded. कोई मुझे अभी बता सकता है कि ये कौन सा ब्रिज है?
Oh yes, ma'am. ये तो Golden Gate Bridge है.
Very good, Neha. Yes, this is the Golden Gate Bridge, which is situated in San Francisco. But if you will observe it now, you may see that the paint is coming off from the bridge. This is giving an open passage to corrosion. क्या आपको पता है हर साल crores of rupees से भी ज्यादा इस पर खर्च किए जाते हैं इस ब्रिज की मेंटेनेंस के लिए?
मैम, सारे मॉन्यूमेंट्स आयरन पिलर की तरह क्यों नहीं हो सकते?
Rahul, I agree with you and I wish that too. But remember students, corrosion is a very complicated process. It depends on chemistry, environmental conditions and many more factors. Look at this. This is another example. Old iron bridge which is in China. See how badly it got corroded. This even got collapsed in the year 2000, which is really bad for all of us. Now I will tell you one last example. Look at this. Can anyone tell me what is this monument?
Yes, ma'am. I have read about this. This is Statue of Liberty.
And can you observe the color and tell me what color it is?
Ma'am, this is easy. It is only copper color.
But if you will see the color now, it is not copper. It is blue-green. And you know that has happened over time from 1886 to now. The color has changed so much.
Wow! Ma'am, this is like magic. What happened?
Yes, students, it is like magic. Copper was the primary component of the statue, which underwent corrosion from air. And remember, this has not happened overnight. It is a very slow and prolonged process, as I told you in the beginning. You see, all these reactions on the board? Initially, copper metal reacted with oxygen, which turned into copper oxide, which is red in color. And then black, and then green, and then blue. So the green-blue color which you see today for the Statue of Liberty is the result of so many chain reactions.
But ma'am, क्या आगे भी इसका कलर चेंज होगा?
No students, it won't. Fortunately, the formation of the blue-green substance on that Statue of Liberty creates a protective layer on the surface and it prevents it from further corrosion. अब मुझे कौन बताएगा कि corrosion कैसे रोका जा सकता है?
मैम, प्रोटेक्टिव लेयर से.
चलो, अब एक फन एक्सरसाइज करते हैं. आपको ये बताना है कि इनमें से कौन सा ऑब्जेक्ट corroded है. So यहाँ पर दो झूले हैं. Which one is corroded? Right or left?
Right, ma'am, right.
Very good, students. Correct. Next time, when you visit any monuments or go outside, just find out which are the objects which are corroded and which are not. Okay?
Dear esteemed organizers, speakers, and participants of the web conference, Namaskar to all. The event of virtual Pincon, Pipeline Integrity Conference by NACE India, is very heartening as it proves human resilience during the severe negative situations like a pandemic and adopting IT as a new way of work and life. Pipelines are like arteries of economy supplying crude oil, petroleum products and natural gas to every nook and corner of geographies. Corrosion in pipelines may result in great loss to economic progress. As per NACE International's landmark study, Impact, done in March 16, India loses 4.0% of its GDP, that is around rupees 8 lakh crore per annum, due to ill effects of corrosion. By employing available corrosion mitigation methodologies, we can save around rupees 3 lakh crore per annum, that is to the tune of 1.5% of GDP. The theme of this conference, Secure Metal, Ensure Capital, is very apt and to the point. With renewed focus on self-reliance across the globe, the ideal of Atmanirbhar Bharat or self-reliant India can be realized by knowledge sharing and capacity building of working professionals about existing and upcoming products and technologies. This conference would serve as a great opportunity for participants from academic and research institutions as well as public and private sector organizations to network and connect with each other. I convey my sincere wishes that the participants experience the joy of learning and interacting with eminent professionals. Best wishes for this event. Thanks. Stay safe, stay protected.
Dear participants, pipeline integrity for a sustainable future should be treated as a priority by whole hydrocarbon industry. Pipeline integrity management is essential to keep pipelines up to date in order to have risk-free and safer operation. This is equally applicable to onshore as well as offshore pipelines. This involves periodic visual inspections, ensuring appropriate cathodic protection, monitoring coating condition and intelligent peaking at regular intervals. Ensuring continuous updation of database with all relevant information obtained during pipeline health monitoring is another requirement. The year after year accumulated information will enable us to operate the pipelines at optimum capacity and in timely maintenance of pipelines. Timely identification of corrosion and in-house implementation of mitigation measures will surely boost our confidence. The codes, standards and regulations governing the pipelines industry are continuously evolving in response to lessons learned from various industry failures. Sharing of knowledge and technical know-how through this platform of Pincon 2021 will provide ample opportunity to deliberate on solutions to many unsolved challenges. It will not only help in saving our assets but also avoid any untoward incidents, thereby protecting our environment. My best wishes to all the knowledge partners of this conference.
Welcome back. Our first speaker for the next symposia on marine corrosion is Mr. KB Singh, who is a specialist and consultant in pipeline coatings and cathodic protection. He has published various technical papers in NACE and other journals and provides trainings on coating and cathodic protection.
He is going to present a paper on corrosion protection of reinforced concrete foundations and piling in coastal and marine locations. KB sir, please.
Good afternoon, session chairs and all the participants. I thank Pincon being organized by NACE Northern Chapter along with Indian Oil Corporation to allow me to present corrosion protection of reinforced concrete foundation and piles in coastal and marine locations. So I'll be spending about 15 to 20 minutes discussing on the protection of reinforced steel in concrete structures. As all of you are aware, coatings and cathodic protection are used for protecting buried steel structures in cross-country pipelines. In the last 15 to 20 years, protection of buried piping systems has also become an important element in protecting the integrity of piping systems of refinery, petrochemicals, fertilizer plants in India. One area which is now gaining a lot of importance is corrosion protection of steel reinforcement in concrete foundations, specifically in piles which are driven into the ground for ground consolidation, for building tank farms, for building structures over grounds which require reinforcement. Also, foundations which are being built for various equipments in a refinery or in a petrochemical plant. Also, the importance to protect the reinforcement from corroding has gained a lot of importance in India. If you see on the slide on the left-hand side, you can see steel rebars, one which is severely corroded, the other which is mildly corroded, and then there is a rebar which is not corroded. So the discussion today for the next 15-20 minutes would be to ensure that the rebar which provides integrity or the structural integrity to a concrete pile or a concrete foundation is maintained by ensuring that the rebar does not corrode with time. When the concrete structure or a pile is in ground, just like in the case of a pipeline, it is in contact with soil. Now, soil has elements which cause corrosion. All of you know that constituents in the soil, oxygen, moisture, ions like chloride ions, sulfate ions, are elements when they come in contact with steel, starts the process of corrosion. Same way, when steel is embedded in concrete, the steel develops a passive layer due to alkalinity of cement. Now that passive layer prevents corrosion, and normally steel would not corrode with time. But specifically in coastal and marine locations, the constituents of the soil contain chlorides, which are one of the major factors which cause corrosion on the steel rebars. Once the corrosion starts on the rebar, as you will see in my subsequent slides, the steel, the rust which is formed on the steel expands, and that causes cracks in the concrete surface. Now, the outside of the concrete surface is in contact with the soil. So when the concrete cover cracks, moisture, oxygen, including chloride ions, penetrate into the concrete foundation and start accelerating the corrosion. And then what happens? If you see on the left-hand side, you can see extensive pitting to severe pitting on the rebars. So the steel rebars start to lose their strength, and that, if it goes unchecked, can lead to a possible collapse of the concrete structure, leading to failure of a concrete structure. And all of you would have heard in the past that in coastal areas, steel reinforced bridges collapse. The reason why they collapse is primarily due to corrosion of the rebars. The concrete structure does not have strength to hold itself and it collapses. Same way in refineries, specifically in the coastal area, as India is building a lot of new infrastructure, the pile caps which support above ground storage tanks, heavy equipment, need to be properly protected so that the rebars do not corrode, which can compromise the integrity of the pile caps or integrity of the RCC piles and thereby endanger the structures like tanks which are built from collapsing, and hence ensuring in today's environment a proper corrosion protection of the steel rebars is extremely critical. As I said, reinforced cement concrete is highly stable because the reinforcement in the concrete becomes passive due to the alkaline environment of the cement. So now in normal cases, the steel reinforcement should not corrode. The cement acts like a coating to the steel rebars which are embedded in it. But due to material limitations, design and construction practices, severe exposure conditions of the soil, wherein if you have a lot of chloride ions which are available, the ions penetrate into the concrete cover and starts the deterioration process of the rebars. And as rebar corrodes, its volume increases, it cracks the outer surface of the concrete and allows moisture, chloride ions, and other corroding ions to come in contact with the steel, leading to a rapid corrosion of the steel rebars. So the photograph on the left-hand side, you can see the cover of the concrete has completely gone. The rebars are exposed to the environment. In this particular photograph, the rebars are exposed to the atmospheric environment, which also causes a high corrosion rate. So this is the process which, as professional engineers, we have to stop. That means we have to stop the reinforcement, the steel reinforcement in the concrete from not corroding to ensure the integrity of the pile caps, pile foundations, and equipment foundations in coastal and marine locations. Normally, as I said, steel in concrete does not corrode because the cement provides a natural protective film which prevents the steel rebar from corroding. The elements which cause corrosion on the rebars are primarily three: chlorides. Chlorides destabilize the passive film, leading to a localized breakdown and causes a rapid corrosion on the rebar. Above ground, carbon dioxide in the air basically penetrates through the concrete cover. It lowers the pH environment around the steel rebar, which loses the passive, causes the loss of the passive film on the rebar and again starts the process of corrosion. The third element in refineries which can cause corrosion on the rebars is DC stray currents. As I said, now in refineries, cathodic protection of buried piping has become prevalent. Now, while protecting the buried piping in a refinery or in a petrochemical environment can cause DC stray current corrosion on reinforcements, concrete reinforcements which are near the anodic gradients. So if proper design is not done of the cathodic protection of the plant piping, it can endanger the concrete piles, the pile caps, which would be in the anodic gradient of these anodes. So the design engineers should be aware that while you are trying to protect the buried steel piping or trying to protect the tank bottoms of large storage tanks, we can cause stray current corrosion on the concrete nearby structures, leading to a rapid deterioration of these structures. So these three factors should be kept in mind while ensuring that the steel rebars do not corrode and to ensure the long-term integrity of concrete structures in a refinery or in a petrochemical environment. So typically, this slide gives you an idea. There is a rebar which is embedded in concrete. The rebar is showing no corrosion, and the integrity of the concrete structure is well maintained. Due to chloride ions over a period of time diffusing through the concrete cover, this is the concrete cover over the rebar, starts the process of corrosion. When corrosion process starts, the rust pushes the concrete up, leading to formation of cracks. When cracks get formed, it forms a direct path of the outside environment, which is primarily soil, to leach into the foundation and start accelerating the process of corrosion on the steel rebar. The photograph on the right shows you structures which are concrete structures where varying degree of corrosion has occurred on the rebars and causing in the one of the concrete structures, the entire concrete cover has fallen, causing rapid corrosion of the steel rebar. So once the steel rebar snap, the structural integrity of the concrete pile will be compromised and it can lead to a collapse of the pile. The photograph on the right-hand side bottom categorically shows various forms of rust which are formed on the rebar. And if you see ferrous hydroxides, the volume is almost 6 times of an Fe ion. Now, as the volume of ferrous hydroxide is 6 times, it causes immense cracks to be formed on the concrete cover if the corrosion process starts, and that what starts basically water chloride ions to ingress and start a very rapid corrosion of the steel rebars. If you see the photograph which I am showing on the left-hand side, the concrete has almost a 4-inch concrete cover. If this concrete cover cracks, chloride ions will penetrate and will start a rapid corrosion of the steel rebars, leading to an integrity issue of this pipe. Now, this slide basically gives you an idea what I've been talking, that how the rebar corrodes. On the left-hand side is the first photograph which is showing you a rebar. It is indicating a passive layer which is built due to the cement around the rebar. Over a period of time, the buried structure, chloride ions diffuse, and on the atmospheric side, if the structure is partly buried and partly into the atmosphere, carbon dioxide in the atmosphere diffuses to the concrete. Both these basically damage the passive film and starts the process of corrosion. Chloride ions obviously start the corrosion process much faster as compared to the carbon dioxide impregnating through the concrete in the atmospheric zone. So when the chloride ions impregnate, they form rust. The rust, as I said, is 6 times the volume of an Fe ion. That pushes the concrete and starts the formation of the cracks. Now this becomes a repetitive cycle, causing the concrete to crack and then eventually fall down. This is being shown in the 3 photographs on the bottom side. If you see the first photograph, the concrete of a foundation post is completely okay. Over a period of time, you can see small crack formation. And then finally, the entire cover of the concrete has fallen down, exposing the steel to the environment. Once the steel gets exposed to the environment, this is what is going to happen. The diameter of the rebar starts to reduce, and then eventually the reinforcement steel will collapse, causing the collapse of the concrete structure. This photograph exactly depicts what I've been telling you. You can see how much is the reduction of the thickness of a rebar. So once this gets compromised, the entire concrete structure can collapse, as you would have heard in India many times. In Goa, we have seen bridges collapsing. It primarily collapses due to the reinforcement getting corroded in a saline atmosphere, and hence the necessity to ensure that steel in concrete does not corrode with time. The photograph on the right-hand side basically shows diffusion of chloride ions through the concrete hitting the rebar. The moment chloride ions hits the rebar, corrosion starts. Now this photograph again shows or conveys the same message which I have been discussing. Moisture enters through the hairline, rust begins to form. Rust, which is ferrous hydroxide, basically has 6 times the volume of the initial formation of the rust. This pushes the concrete up and causes a complete breakdown of the concrete cover, exposing steel directly to the environment, leading to either crevice corrosion or pitting corrosion. Now both these corrosions have a very high corrosion rates. They are not dictated by normal corrosion rates. The corrosion rates can almost be 0.5 to 1 millimeter per year, and if the rebar is about 16 millimeter or 25 millimeter, in 10 to 15 years in corrosive environment, the rebar diameters can reduce considerably, which would compromise the strength of the concrete, causing a catastrophic failure. Now, how do we check a concrete which is embedded partly in the ground and partly in the air? whether the rebar is corroding or not. So we all understand the science of measuring in our terminology, what we do, pipe to soil potential. The same terminology or the same systems are used for checking what is happening on the rebar without removing the concrete. ASTM C876 provides a relationship between the measured potential values and the corrosion probability. So what we do is we take a sponge, we take a copper sulfate reference electrode, put the sponge on the concrete, put the reference electrode in a copper sulfate solution so that a proper electrical connectivity is made between the concrete and the copper sulfate reference electrode. The copper sulfate reference electrode is connected to the multimeter the same way we would connect a pipe, and the rebar is connected to the positive of the multimeter the same way we would connect a pipeline. Now, the potential what we read, if the potential is more negative than minus 200 millivolt, the probability of steel corroding is less than 10%. If the rebar potential is more electronegative than minus 0.35 volt or 350 millivolt, then the chances of steel corroding is more than 90%. Within 200 and 350 millivolt, it is uncertain if the steel is corroding or not. So by doing this simple test, we can really find out if the concrete within, the rebar within the concrete, is it in a passive zone or is it in an active zone as far as corrosion is concerned. Now, the way we have potential ranges of steel in soil, where we know that between minus 0.3 to minus 0.7, steel is corroding, but potential of minus 0.3 volt in steel shows that the steel is cathodic, and minus 0.7 shows that the steel is anodic. Same way, by measuring the potentials of steel in concrete, we can find out what is the condition of the rebar in concrete. So depending on the status of the concrete, it can either be humid but chloride free. So if we measure potentials between minus 200 to plus 100 millivolt with respect to a copper sulfate electrode, it gives us an indication that the concrete is chloride free. If we are measuring potentials between minus 600 to minus 400, we know that the chloride is contaminated. If we are measuring between minus 1000 to minus 900, the concrete is saturated with water, but there is no oxygen. And then if the concrete values are between minus 400 to plus 100 millivolt, the concrete is carbonated. And similar, we can find out if it is a dry concrete or if it is a dry carbonated concrete. So if it's a dry concrete, we will have a potential of 0 to plus 200 millivolt, and this indicates no corrosion. So by logging in these values of the potential of steel in concrete with respect to copper sulfate electrode, we can find out the status of what is happening in the rebar, the same way we do measurements of pipe in soil. This is a very important test to be conducted by engineers to ensure that the steel in foundations or steel in pipe caps are not corroding. Now, having determined what is the status, we now have to look into mitigation measures. Typically, the story is same as we do in pipelines, but what we do in pipelines, we have a coating. Apart from coating, what do? We apply cathodic protection. So if you apply the same story onto a rebar, which is embedded in concrete, the corrosion protection mitigation measures of rebars becomes very easy to understand. So this is a rebar casted in concrete. This is basically the distance between the rebar and outer surface of the concrete is called as the concrete cover, and it is embedded in atmosphere where chloride ions are floating around, which can either be soil or it can be an outside atmosphere. So how do you protect the rebar? Either you do a coating, or you apply cathodic protection, or you do a combination of both. So that's one strategy. The other strategy is to apply a coating on the concrete surface between the concrete surface and the soil. So this is another strategy. Another strategy is to put in corrosion inhibitors, which would not allow corrosion to occur on the rebar and will keep rebar in the passive state. We can also put in some chemicals within the concrete, which would reduce the permeability of the concrete. That means it would not allow easily chloride or sulfate ions to move from the soil into the concrete and hit the rebar. So these are various strategies which can be adopted to prevent corrosion of rebar. So the basic strategies which anybody would adopt is to use a high performance concrete which would inhibit moisture chloride ions hitting the rebar, provide coating between the concrete and the soil surface called as concrete surface protection. The third strategy would be to do a rebar coating. That means you coat the rebar. The fourth strategy would be to do cathodic protection of the rebar. And the fifth strategy would be to put corrosion inhibitors in the concrete, which would keep the surface of the rebar passive. Now, I will not go in detail on this slide, but it gives you various strategies which can be adopted in all these 5 points which I have discussed: high performance concrete, concrete surface protection, rebar coating, cathodic protection, corrosion inhibitor. Within these 5 strategies, we have different sub strategies which can be adopted to ensure the integrity of steel rebar in concrete. I will be basically focusing on FBE coated rebar, which is being commonly used now in India, a galvanized rebar which has also been used. Along with, I'll show you some slides of how to do impressed current protection of rebar in concrete. So the first strategy which a company would look in is to use a high performance concrete which would inhibit chloride, oxygen and moisture to travel into the concrete cover and cause the loss of passive film of the rebar. So again, there are various strategies which can be used to have a proper water cement ratio, to provide adequate cement cover, to have a high range water reducing admixture, curing the cover properly, and having a proper cement to water ratio, which I already mentioned above. The objective of this strategy is to slow ingress of corrosive elements into the rebar. Now we can reduce this by about 10-15 years, but eventually through the concrete, these corrosive elements will hit the rebar and cause corrosion. So this is a mid-term strategy. It's not a long-term strategy. The other strategy is to apply coating, which we typically call as surface sealers and membranes in this technology. So these membranes, which is basically a coating, will not allow oxygen, chloride, and again, water molecules to hit the steel surface. There are various types of sealers which can be used depending on the life and the cost. What is the objective? To block corrosive elements at concrete surface. Material selection. We can have a normal rebar. We can have a corrosion resistant rebar. We can have a fusion bonded epoxy rebar. We can have a galvanized rebar. Mostly for buried structures, fusion bonded epoxy rebars are used. Galvanized rebars are normally used for atmospheric conditions. Corrosion resistant rebars are also not used for buried applications. They are normally used for above ground applications. Objective is to ensure that steel is not exposed to the corrosive environment the same way we do 3-layer PE or fusion bond epoxy on our buried pipelines. So this photograph shows FBE coated rebar, commonly known as green rebars. Effectively can be used to mitigate corrosion. During construction, we have to be very careful that when bending the rebars, if the FBE cracks and expose steel to the environment, we can have accelerated corrosion. So proper construction care is
Sir, your internet is breaking.
In this strategy.
Sir, your internet is breaking.
A galvanized coated rebar is typically used for above ground structures. It can effectively mitigate corrosion on 30 to 35 years of the structure. We can,
Sir, your internet is breaking in between. Can you restart from the green rebar, sir? No, time is not up, sir. The green rebar, sir, everything was, there was...
If oxygen, chloride, moisture enters the concrete cover, it would not cause corrosion on the rebars. Now this has a limited duration, can protect the rebars for 10-15 years, not a long-term solution, but this is also used on many structures which are being rehabilitated. So a consultant has to decide which anodic and cathodic polarizers they want to use. But as I said, the life is limited. Now, a commonly used system is using cathodic protection. As all of you know, we have either impressed current cathodic protection or we have sacrificial cathodic protection. Both technologies are used for preventing corrosion on the rebars. An impressed current cathodic protection, we can use anodes which are embedded in the concrete, or we can use anodes external, that means it is kept in the soil. For structures which are above ground, ICCP is a very common technology. Obviously, when the structures are above ground, the only option available is to put the anode within the concrete. You can't put it outside because there is no means for the current to get delivered in an atmospheric condition. The sacrificial systems are also used, but they have a limited life and they are embedded within the concrete. So on the left hand side, the photograph is of a MMO mesh anode. On the right hand side, the photograph is of a zinc anode embedded in concrete. In both these solutions, the anodes are embedded within the concrete. This photograph particularly shows sacrificial anodes which are embedded within the foundation or within a pile. Each anode has a limited area. It will not cover a very large area. It would typically cover 1.5 to 2 square meters. So if you are using a sacrificial system for protecting your structures, you need to be very clear that it will only protect about 1.5 to 2 meters square. So a large number of anodes have to be embedded in the concrete. The photograph shows, you can see in a small area, they have embedded almost 5 anodes, 5 zinc anodes. There's also a solution where you put a zinc mesh around the pile cap or pile foundation if it is above ground, and then we put concrete layer over it so that the zinc mesh gets embedded. The zinc mesh is connected, electrically connected to the rebars, and the zinc mesh continues to provide current and sacrifices itself but does not allow the rebars to corrode. You can see again some photographs of zinc anodes which have been embedded on a structure where the rebars have completely been corroded. So this is the zinc anode. Around the zinc anode, a synthetic woolen cloth bag with a backfill, the way we provide bentonite gypsum in our zinc or magnesium anodes which are embedded in soil. Same way we are putting in a backfill which would retain the moisture and allow the zinc anodes to deliver current to the rebars. So here the concrete has been removed, the anodes have been installed, and the area will be repaired by putting in cement. Now these anodes will prevent further deterioration of the rebars. Coming on to cathodic protection, as I said, there are two strategies. Either we put a rebar, a MMO mesh anode in the concrete. So the blue color is an anode which is embedded in the concrete. On the right hand side, we have a MMO tubular anode which is embedded in soil. The strategies of both the anodes are to deliver current uniformly onto the rebar. When you put in a mesh within the concrete, we get a uniform current distribution because the mesh anode is very close to the steel rebar. When we are putting in a MMO tubular anode in soil, the design has to be proper to ensure that there is a uniform distribution of current on the rebar. Otherwise, the impressed current system will not work properly. Only a certain element of reinforcement will get protected, and the other areas of rebar will not get protected. So for soil-based anodes, a proper design has to be done to ensure a uniform distribution of current in the concrete structure. Now this photograph basically shows reinforced, in the reinforcement, MMO mesh anodes which have been installed. The blue color are the MMO mesh anodes which are connected to the positive of the rectifier, and the negative of the rectifier is connected to the steel reinforcement. In the center, we have embedded reference electrodes, which are basically silver chloride reference electrodes, which measure the potential of the rebars. The entire foundations of the Ionic Burj Khalifa Tower in Dubai, the entire structure below ground is protected by ICCP. The whole purpose of providing ICCP was to ensure that the foundation does not corrode for a design life of 80 years. And ICCP is the only solution which would provide such a magnitude of design life. ICCP of using ICCP for cement, for CP of reinforced concrete structures is a very sophisticated technology. There are NACE standards written around it. There are ISO standards written around it. So in case if any asset owner wants to use this technology, proper designs are required, and it's a mature technology to protect rebars. Again, some photographs which are being shown where the mesh anodes have been kept on the rebars. On the right hand side, you can see a silver chloride reference electrode embedded in concrete. Now, the current densities which we normally design vary from 0.2 to 2 milliampere per meter square. where the reinforcement is not passive, and we suspect that the chloride ions will continue to impregnate through the concrete into the rebar, then we design based on a much higher current densities, which could range from 2 to 20 milliampere per meter square. So depending on what is the type of soil, depending on what type of concrete we select, depending on what type of rebar we are using, the current densities could range anything from 0.2 to 20 milliampere per meter square. So selecting the right current density is very important in ensuring that these reinforced concrete, if protected by ICCP, remains in a passive state for the entire design life. There is the ISO standard 12696, which can be referred to understand which type of or which how much of current densities are required to be impressed onto a concrete foundation depending on the environment. So this is the end of my presentation. I have discussed which are the various technologies which are available today to protect RCC foundation and piles. The engineers working with consultants and the clients need to understand the entire environment surrounding a pile cap or surrounding piles, surrounding foundations, and then choose a proper mitigation measure to prevent corrosion of steel rebars. So with this, I'll finish my presentation. If there are any questions, I am willing to answer. Thank you, everybody.
Thank you so much, KB sir, for your lovely presentation. Can we have you online, sir? KB sir, are you with us? That was a very informative session, Mamta. Yes. Especially on reinforced concrete foundation. This was the first presentation that we had on the reinforced concrete foundations.
And we would like to, like all the participants, they are requested to post their questions in the chat box so that we may discuss it with the speaker.
I think KB sir is trying to join in. We'll wait for a couple of minutes. Yeah, hi KB sir. He's trying to join in. Wow, so many questions. I'm sure sir will love to have them.
I would request our technical team to please help KV sir if he is facing any problem. KV sir, can you hear us? Looks like he is going to join.
This is the new normal, Mamta.
It is indeed.
We also have received a message from our technical team. Yesterday, many people faced difficulty while logging in, and we understand that it might have caused inconvenience to you. However, you will be glad to know that you are part of a complete 3D immersive platform developed by Exporium. This is India's first ever complete 3D immersive virtual technical conference along with an exhibition. You can explore these platforms from any device, be it a touch screen, be it a mobile, laptop, tablet, or iPad, and in any processor, any speed and any moderate internet connection. The 3D design is modern and innovative, and each sponsor and exhibitor has an exhibit which is beautifully designed and is 360-degree viewable.
Please take time out to explore the exhibition and meet the sponsors and exhibitors during the breaks. Also, please note that the exhibition is open for a week and is free to access and explore on www.nzpic.org. So don't forget to visit the Pincon Expo.
One more interesting figure that we have over here is, you'll be all glad to know that we had record numbers at the exhibition yesterday, peaking at 2,500 in the lobby area. We had almost 1,500 visits. Okay, we have KB sir with us. Hello.
Can you hear me now?
Yeah, yes, sir. We are hearing you. How are you, sir?
Fine. Good afternoon, everybody.
Good afternoon, sir.
Not a bit difficult to get in.
This is the new normal, sir. We are all getting acclimatized with it, sir. Not an issue at all. First of all, sir, very nice presentation from your end, sir. It was very informative, very explanative, sir. And we have many questions, sir. So would you want me to take them one by one, sir?
Yeah, just take it. We have got 10 minutes. I'll try to do. Otherwise, whatever is left off, I'll send replies afterwards. So you can start now.
Sure, sir. Thank you so much, sir. The first question is, sir, corrosion inhibitor can be used in a rehabilitation of a reinforced concrete foundation instead of CP. Is it true, sir?
Yes, it can be used. But as I said in the presentation, it has a limited life. Depends on which type of corrosion inhibitor you select. It will make the steel rod passive. Then the life is limited. Could vary anything from 10 to 15 years.
Okay. The next question that we have is, sir, in order to mitigate measures of concrete, is barrier coating desirable over a CP system?
In case if you are not installing CP systems, a barrier coating will definitely help. If you see today the current specifications in India, a bitumen paint or a bitumen sort of a wrap is applied on the external side of the concrete foundations. You can't apply it on a pile, but on foundations you can apply it. But again, a limited life. Once bitumen loses its dielectric properties, water, if it is chloride infested, will hit the rebar in a course of time and start the corrosion process. So again, a limited strategy for a limited time duration.
Okay. So the next question is, what would be the typical current requirement for the ICCP system for concrete structures?
No, I've given the current densities. The current densities can vary anything from 0.2 milliampere per meter square to 20 milliampere per meter square. But over a period of time, as the rebars polarize, the average current densities would be of the order of, during the operational stage, would be of the order of 2 to 4 milliampere per meter square.
Okay, sir. The next question is, how would you design a CP system for a RCC structure?
An RCC structure design, this is what I've discussed. Basically, two type of designs. Either you put the anodes within the concrete foundation or pile, or you put the anodes outside in the soil. The preferred technology to ensure that there is a uniform current distribution is to put the MMO mesh anodes within the foundation. So we work out the current density, then we work out based on the current density how much of MMO mesh anode is required. There are softwares which decide the distribution of the current, and accordingly the placement of mesh anodes are decided within the reinforcement, and then the concreting is done. If we are going external, then and if it's a plant environment, then we have to be much more careful in terms of ensuring that there is no interference with the other metallic structures if they are not cathodically protected. So both the designs are adopted. Standards cover both aspects of cathodic protection. Decide a technology and then design it accordingly.
Okay, sir. The next question is from Mr. Deepak. He asks, how semi-deep well can be used for ICCP protection of rebars?
Okay, a semi-deep well is what I have just spoken. It is a anode system in the soil outside the concrete cover. So when you start putting in semi-deep, it will distribute the current. But if you have, say, a bunch of piles, say about 30-40 piles, and then you have a pile cap, And if you are putting in semi-deep outside that mesh of piles or a cluster of piles, we would find it difficult to do a uniform current distribution. Semi-deep wells, if there are many piles, it's very difficult to ensure that the piles in the center would achieve or would receive current. Again, a lot of experience and a lot of expertise is required how to locate the semi-deep well to ensure that every single rebar in that pile configuration is protected. Yeah, next question.
The next question is how to detect steel rebar's corrosion for cement concrete surface.
No, again, it's a good question. In one of my slides, I had shown it's basically a copper sulfate reference electrode fitted with a sponge. So you put it on a concrete surface, connected the way you would connect it normally to a multimeter. And if we are reading the PSP, or this will be concrete rebar, to reference cell readings anything between -0.4, -0.6, it indicates that the rebar is corroding. A rebar is in a passive state if we are getting a reading between -0.1 to -0.2. That shows that the rebar is protected. If your rebar potential is between -0.4 to -0.6, rebar is corroding within a concrete. If you are from one of the plants, you can do this testing and find out if your rebar is in a passive state or in an active state.
Right, sir. We'll take a couple of more questions, sir. The next question is, what should be the choice between epoxy coating and CP protected bare steel, and what reference monitoring is recommended?
Okay, if you are going in with FBE coated rebars, normally CP would not be applied because it would only add to the cost. These technologies are not cheap, they are pretty expensive. So the choice would be between an FBE coated rebar or what we call as a black rebar with cathodic protection. The FBE coated rebar is being used quite a lot. We have to be very careful that we do not damage the FBE when we are bending the bars. As long as we don't damage the FBE, it will last for quite some time, 30, 25, 30, 40 years, your design life. But if you are cracking the FBE at the bending, then those points would become highly anodic and would be susceptible to a very high rate of corrosion. A cathodic protection system ensures that the current is uniformly distributed. And we normally put in, as we said, silver chloride reference electrodes to monitor the pipe to soil potential of the rebar in a concrete.
Okay. One last question, sir. What is the life of these sacrificial protection?
A life of a sacrificial protection anodes, which are basically zinc anodes, could vary anything between 3 to 5 years. Beyond that, the zinc anodes have to be reinserted in the concrete and the concrete has to be restored. So it's again a short duration process, but it is used in many of the buildings, in many of the foundations in the buildings where impressed current cathodic protection would be very, very expensive. So every 5 years, the zinc anodes are then again replaced.
Okay. Sir, we have 2 minutes left. Can we take a couple of more questions, sir?
Yeah, please do.
Okay. There is a question by Mr. Agarwal. He asks, will the reference cell kept on the concrete surface give true potential of the steel bar? Is it not required to keep the reference cell close to the steel bar itself?
No. There are two ways. One way is a permanent reference cell. Permanent reference cell, the way exactly we do in pipelines, has to be embedded in soil. So a permanent reference cell has to be embedded in concrete. A reference cell with a sponge is something like a portable reference cell, which is put on the external surface of the concrete to measure the potential. So same technology as we used for pipelines, permanent and portable. Same thing gets applied on concrete also.
Right, sir. Thank you so much, sir. You have patiently answered all the questions, sir, and shared your valuable inputs. Thank you for your time, sir.
Thank you very much. And
have a great day, sir. Bye-bye. Take
Wish
care.
everybody to enjoy this technical symposium. Thank you very much. Thank you all.
Thank you, sir. Bye-bye, sir.
Our next speaker is a senior scientist from CSIR, Central Electrochemical Research Institute, CECRI, Dr. Rakesh C. Barik, who is a specialist in corrosion. He holds a PhD from University of Southampton, UK.
He's going to present a paper on erosion-corrosion performance of copper-based alloys for marine environment. Dr. Barik, please.
Hello everyone, this is Dr. Rakesh Barik. I thank NES Gateway India section for giving me an opportunity to talk about a marine corrosion session on erosion corrosion performance of copper-based alloys for marine environment. I know this is a very difficult situation for everybody in this corona pandemic period, but however we are going to continue the discussion and keep on going to work on corrosion, and we will be, I think this research and our contribution to the field of corrosion science will be continuing, though we are not able to meet up, but I'm sure we'll be meeting very soon and we'll discuss the idea in person. So okay, I'm going to talk about this topic, which is one of the, though NES is talking about this pipeline, but here also I will be talking about one of the parameters of the pipelines is the flow corrosion. So I will just talk about some materials which is being used for heat exchanger pipes or maybe drinking water pipes in in a chemical industry or in the oil and gas industry, which is being accelerated its corrosion in presence of a aggressive environment. I think I don't need to introduce myself. I'm from CSR, Central Electrochemical Research Institute, Karaikudi, Tamil Nadu, and this is well based in close to Trichy and Madurai, and we do a lot of work in various types of corrosion. So one of the area I focused into the erosion corrosion. So what I'm going to talk about this topic is, this is a copper-based alloys, and we all know that it's a very widely applied in the naval application or in the marine condition. But however, the pure copper is not much being used. But when it comes to alloying element like copper nickel, aluminum bronzes, or nickel aluminum bronze, which is nothing but a copper-based alloys, which has extensive application in in the marine environment. If you look at these components I have here, like valves and fittings, ship propellers, pumps, shafts, valve stems, heat exchangers, and water boxes. So these are the these are the wide application of this of these copper-based alloys. And here I have a properties. For example, when you look at a component, if it's in the open seawater or in the dry dock condition. So there, what are the property can influence your corrosion behavior? Whether it could be shear stress, or it could be the the mass transport due to the flow corrosion, or being having the protection strategy like cathodic protection, or the various environmental parameters like temperature, salinity. So these are the, but all these properties can vary from one place to another one. So that's why these components are being affected by the operational cycles, which is very tricky when you choose this copper-based alloys for a marine-based application. And but well, in this particular research, what I did actually, I took a nickel aluminum bronze, which I'm going to talk about the composition and all that. So in that I studied mostly the flow corrosion, erosion and erosion corrosion behavior, and I compared with a alternative called it's a coating actually. The coating the coating was achieved using a GVOP coating. It's called high velocity oxyfueling process. In that I coat this nickel aluminum bronze materials on the surface of a cast on the surface of a mild steel to achieve this cast nab property. So now we'll see when we go towards in our the presentation, we'll see how it behaves. So this is the actual composition of the cast nab. If you look at here, the major component is the copper. Copper is the but the nickel aluminum bronze. But though its name is bronze, but it doesn't have any tin content. But this nickel aluminum bronze contains major component like nickel, aluminum, and iron. we can see aluminium comes to 9 to 10%, nickel and iron like 5 to 6%, and the rest of the elements are like chromium, and you'll be having some balanced copper. Then I'm comparing with the NAB coating, which is being done using a a spraying gun, diamond jet HBOP spraying gun, and that is coated on a bare steel surface, which is 436 steel, and being also compared with HPO. This is only aluminium bronze, where you have a variation in the composition of all these aluminium, nickel, and iron. In addition, some other components like molybdenum and steel. But this but the wonderful things about this alloy is it's a microstructure which is having a various different phases, 5 different phases, alpha, beta, kappa. Because we know that in the moment, because of these different phases, it has a very chance of going selective phase corrosion. It means, like we know that in case of your brass, where you have a copper zinc alloy, the zinc is the selectively goes because it's highly electrochemical active compared to copper. So similarly, here the phases, we have to see the alpha phase, which is rich in copper, it preferentially corrodes in seawater, which have been seen in this condition. So now I'm going to see these behaviors in a erosion and a corrosion environment. So I just want to, before I go and talk to the basics of erosion and corrosion mechanism, here I will just talk about the basics of a copper metal when you immerse in a chloride environment. But if you look at here, for example, like you take a piece of copper and immerse in chloride environment, the major cathodic reaction is the oxygen reduction. So this is the oxygen reduction happens, and you go to OH minus. It involves 4 electron process, and the further complexation of chloride with copper, you get a copper chloro complex, and that copper chloro complex can form a cuprous oxide. So this is very tricky here. These experiment, the setup of the formation of this cuprous oxide, or that transformation of that cuprous to cupric, we only encounter in a metal like on copper only in a static case. But the moment we go to flow condition or the erosion corrosion condition, this formation of copper oxide is being limited and doesn't form actually, that we will see in one of our example. But here I have a base copper metal I have here, and in this, if you see here, that is our classical anodic reaction. The electron leach out from the releases from the copper, and it reacts with the this oxygen and water which is in the bulk media, and it forms a cuprous ion, and the cuprous ion can react with the chloride complex for a cuprous chloro complex. Then it forms a lot of precipitates, like what do you call the green color precipitates. You end up in having an atacamite. But all these phenomena, we see them in when there is a static environment. But the moment we go into flow condition, that is become changes. That we'll see. But here, the other one was a pure copper. Now I'm talking about corrosion mechanism of the NAB. There's a nickel aluminum bronze. But you can see below the substrate, I have a this because this is I already told you this nickel aluminum bronze. Once you expose it, it has different layers of oxide film formation. One of the good thing about this alloy is formation of your Al2O3 rich layer, and this Al2O3 rich layer is actually hinders the transport of this copper ion through the to the upper surface or to the bulk liquid, and it prevents the corrosion. But this is what we see. In addition to copper, you'll have another layer called aluminum oxide. Now I'll go into my experiment, which I have been carried out for this particular work. One is the first experiment is corrosion. That is nothing but called flow corrosion, where I have a liquid of say 3.5% of sodium chloride solution is passing through that is creating a jet and go and impinge on the surface. That is velocity 3 to 6 meters per second. Then I go to erosion. But in the erosion is nothing but a mechanical process. Like for example, like you talk about preparing a surface for like a painted surface. You do sand blasting or grit blasting. What do? You try to remove some some sort of corrosion product from the surface. So this is also similar process. It is a mechanical. There is no corrosion effect. Even I am having a sodium chloride solution, So what I'm doing, I'm suppressing or completely eliminating its corrosive nature by holding that substrate at a minus 200 millivolt over potential. What I'm calling it cathodic protection. But you could ask me, I could go up to minus 1 volt. But if you go into minus 1 volt, the other complication arises, like hydrogen gas evolution and all that. So in order to prevent that, I just go below the OCP of copper by adding a minus 200 millivolt. So by that way, I'm achieving its erosion condition. Then, but to carry out an erosion, you need a solid particle which will be carried in the liquid and go and impact on the surface. So for that, I used two different size of sand, one 135 micron and another is 235 micron. Then I come to the third one, erosion corrosion. So that is the combination of corrosion plus erosion. So these two combination, what they do, I will run the experiment. Now I remove the cathodic protection from here. So I will, I use same velocity range, 3.1 to 6 meter per second, and at a the size 135 to 235 micron, at a velocity of or the flow rate of 6.3 to 9 per meter, 9 meter second. I carried out this experiment. So how I did this experiment, I will just show you this the rig actually. This is actually the first rig. I use a jet impeachment rig. Here I could we could do all these three experiments: corrosion, erosion, and erosion corrosion. And then the right side I have another electrode setup called a wall jet electrode. This is what I just want to show you. One experiment I will show you what happens, this mechanism, like the formation of cuprous oxide or the cupric oxide, how it varies from a static to flow condition. So this is what I have, because it's a very small cell, and in that particularly we can study the electrochemical, look at the potential dynamic or impedance. We could do that, and I could see not the formation of the any cuprous oxide. That I will show you some results. But here, if I look into this, sorry, if I look into this here, this is a reservoir. I have full of 3.5 sodium chloride solution. Then in that a small bucket is there which contains sand. So what happens through this? There is a pipe. I put it here with a filter, and it pumped through to this assembly, through this setup, the jet impeachment setup. The liquid comes and go and heat. But there is another connection I have given here. It is called a have facilities here. I have created such a way, using playing the different nozzle. I'm creating a vacuum. By creating a vacuum, the ejector assembly which is here, by creating a vacuum, I'm able to suck this sand and maintain a particular concentration of sand, which will go and heat on my surface. So first experiment, I did the corrosion experiment, the flow corrosion experiment, 3.1 to 6 meter per second. When I did that, I isolated the sand, so I was not taking any sand, and now no experiment was not running. Then second experiment, when I did erosion, so sand or the liquid will come through, sand will go there, they mix and form a slurry. But this is very tricky actually. This is the part we need to understand, how this experiment is being carried out. So the sand and liquid get mixed here, and they'll go and hit on your nab surface, which is called working electrode. Then similarly, in the other case, when erosion and corrosion is there, I will also similar experiment I will conduct it. But the moment I do erosion, I only put a cathodic protection minus 200 millivolt extra on the surface, so that way I able to control, because I have a reference electrode here. I am so reference electrode this side, and I have a counter electrode here. So this is the way I was carrying out the experiment. But similarly, I kept my nab nickel aluminum bronze surface here. I had reference electrode here, the counter electrode over here, and there was a gap of 300 micron. The nozzle will go and heat it. This is I was running my both flow corrosion and erosion corrosion experiment. So I just want to talk about, before I go into this experiment, this coating actually, because the whole idea was this particular alloy, nickel aluminum bronze, was we took the cast metal. Then what is the need of this coating actually? Because same composition I deposited on a mild steel substrate, so that the whole idea was to refurbish a refurbishment, or maybe a cheaper alternative of a propeller based metal. So this is what I did coating. You can see that these are all having a lot of particles here, but the only thing is that the porosity was a one issue here, and we had a lot of unmelted particle also, unmelted oxide, and a little bit of a network crack. Some crack was there. That I will show you how it reflected in my results. So this is the test material actually. I have nickel aluminum bronze and aluminum bronze, and we can see that these are the cracks here. So we call the pores and all that, and some of the particles which is not melting. This is the we do a ACM. This is your bare metal, base metal 4360 steel substrate, and all that it was coated. Then we had also some particle like partial melted particles and impurity of of oxides and some splat boundaries. So this is the first experiment result I will I will talk about here. So what happened here, this is called a flow corrosion experiment. There was no sand particle. I just want to talk about. So here if you look at the x-axis, the velocity, and I looked into the corrosion rate. So now I did the cast knob, this green color. You could see that the cast knob was behaving better than your bare substrate, the base, the 4360, the base one, 4360 carbon steel. Then also if I compared with knob. So this was actually, like we also confirmed with the literature, and we saw that the flow corrosion rate, is a little bit of a higher in case of a coating compared to the cast. It was like 0.8 to 1.5 millimeter per year. Then for the cast knob, 0.5 to 0.6 millimeter per year. Then we go to another metal like which is when you talk about the ACM, you could see that the coating had a lot of a lot of attack in the pores damage here, and the electrolyte was able to penetrate, and it was able to create the localized corrosion. Then this was a flow corrosion. I did. There was a corrosion and a flow corrosion I did in my wall jet electrode. What I was trying to tell you, if you look at a static case, this the blue color one, this is formation of a cuprous oxide and transformation of a cupric oxide. But in case of here, look at this. This jet impeachment case, I was not able to see the formation because that cuprous chlorocomplex was not able to precipitate on the substrate and is able to carried away by the flow. So that's why it was not able to prevent its not able to give any corrosion resistive properties. So this oxide film was not able to form. The same thing also I could see here, the jet impeachment is complete dissolution. So there was no cuprous chloride complex was not forming. Then I come to erosion because corrosion, we talk about a corrosion rate that is just a millimeter per year. But when it comes to erosion rate, when I do a sand particle, in that case I put another equation because I'm talking about a liquid, I'm talking about the flow rate of the liquid, then I'm talking about the sand particle. So that is nothing but the slurry which is forming, and the slurry has some size like 135 to 235 micron. So I look into the kinetic energy. So all these parameters I take into and formulate a new equation which we call the volume loss per particle impact. Okay, so now this is the results actually, the volume loss per particle impact, which is called the erosion, and I looked into the kinetic energy. Kinetic energy is nothing but with your velocity and the mass of the particle impinging on the surface. The similar behavior also, the cast knob is here, this is the round one. You can see that cast knob at a very low kinetic energy that also performs better. Erosion rate is less, but when you come to steel, it is very high. Similarly with the coating, it is also very low. This is what we have, we have observed. Then we could see, I'm sorry, you could see here, when the liquid is hitting with sand particle, you can see it creates some edge, the wear on the substrate. You can see that these two, very distinctive feature, it's creating wear scar. Similarly, also in the flow direction, because sand particle goes and heat and it removes the material. This is what we observe. Then we come to erosion corrosion. But when it comes to erosion and corrosion, this is similarly is also, I look at the cast knob. You can lower kinetic energy is almost close to the thermal spread process HBOP knob. But however, as usual, the erosion and corrosion rate also increases for coating material compared to the cast knob. This is, and also and also bare the base 4360 steel is actually very higher. And also we can see, this is what actually very particular. This is actually, if you zoom it, These are the phases. We should talk about the alpha phase getting here, and this is kind of a wear scar happening in the direction of the flow. But when it comes to maximum erosion depth, that is when there is a sand particle is impinging, it's giving kind of a plastic deformation is happening. And also this is also, we have seen the same thing. We can see the the way, so one directional, the liquids hitting along with the sand, and it's creating the wear scar. Finally, what we talk about, we look at a synergy. This is the concept actually very interesting, you have to understand, because the erosion and corrosion consists of three components: flow corrosion and erosion, then total erosion corrosion. But now the synergy is another factor we came. The total erosion corrosion should be equal to E plus C, but it was never. So there is another factor came, it's called S, and that S is the synergy. So that is the difference between that, and that synergy is actually decides if it's a negative, what happens, if it's a positive, what happens. So we have defined that, if you need a negative value, if you get a synergy, that means you are having a, you're giving some extra safety factor for the material. But if it's a positive, that means your E plus C is less than the T. That is what we have seen in couple of cases. What we do, that the ratio of synergy to percentage we have calculated, and here you can see a lot of materials certain erosion rate, or if I look into the lowest kinetic energy, in that study all are negative value. But then when you go on, the impact is increasing, this synergy is going positive side. So that indicates that this material, you have to be it's very sensitive to the and it increasing the corrosion rate. So finally, what we concluded, if I am going to, with these data, what I have done with the copper-based alloys, nickel, aluminum, bronze, in erosion corrosion condition, and I exposed to various velocity. So from the 3.1 to 6 meter per second, I concluded that if this is just an assumption we have taken, and here I have taken a particle diameter 100 micron, but in my original experiment I took 250 to 200 micron. In those cases, if I just assuming that I have a component like pipe, valve, pump, and a propulsor, and I want to know, before I design the component, I know the material, what is the condition they can achieve. So for example, we conclude that up to 3 meter maximum a pipe can be designed. For valve, you can have 5 meter per second. For a pump, you can have 10 meter per second, and a propeller, you have a propulsor system 25 meter per second, only this energy range. So this is the, actually we wanted to come up with an idea that how do you construct a marine based application, a component of using knob. This is what we gave a conclusion. This is the summary of my work. What we did, that the cast knob showed higher resistance than the knob coatings under flow corrosion conditions. Then this coating had a very high sensitivity to impact energy, because of its having a network of cracks plus unmelted particles, then flow density and splat boundary. But however, the whole idea was, we can the whole idea was, if this coating can be used in the low kinetic energy condition, that means when you're trying to refurbish a marine condition. Even from the cast knob also showed that it has a good erosion corrosion performance, lower carrier energy, and negative synergy was found and all kinetic energy for cast knob, which shows that it has some good good properties. And positive synergy was found. That means that is the coating needs to be optimized, and because of its the way it's being applied, so then it can be, the property can be improved. I think I came to the end of the talk. I am hopefully I'm able to give some glimpse about the work on my copper-based alloys, nickel, aluminum, bronze under erosion corrosion condition, because the jet impingement or the wall jet electrode setup which I have here, I've been working on this, and also now looking into the how to inhibit the erosion corrosion condition in the in this in a 3.5% sodium chloride solution. Thank you very much, and I would look for the interaction of the audience.
Dr. Barik, can you hear us?
Can we have you on the line, sir?
Yeah, I'm there.
Yeah.
Can you hear me?
Yes, sir.
Yes,
Absolutely, loud and clear.
Okay. Okay, I think I can see that. Yeah, please.
How are you, sir?
Fine, very fine. This is the first time I'm hearing myself on a recorded presentation. I think I never did actually earlier, but I just want to thank, though it sounded very odd to me, because I always used to, present in front of an audience, but this was the first time. But anyway, I just want to thank Pincon and Gupta ji from IOCL, who, well, I know him very well because he was one of my, organizing, when I organize a conference, he used to support me a lot. So I immediately agreed to give this talk. But I know this is a little bit different for the people from the oil and gas industry. But this is an area where we talk about, copper-based alloys being used for heat exchanger application, valve or pump or any other application. We use that. And I have because I'm like more into academic field, unlike the other speaker who have a lot of experience in the industry and they are into like solving the direct problem. But here we look into more of the fundamental aspects of the corrosion issues, and all these works we do, taking some PhD students and research scholars, they do that. So this was a more of a work which I did in my own during my own study. This is, and also I look, and a lot of the couple students I have right now, they look into preventing the corrosion of copper-based alloys using maybe inhibitor, or I do like changing this various parameter in the pipe flow condition, or maybe design change or a material selection. So this was the entirely I was trying to speak about this about this in this talk. Thank you very much for giving me an opportunity. Thank you.
Thank you, sir. I must tell you, sir, we liked the presentation a lot, sir, even though it was recorded.
Okay.
And we have certain questions, sir.
Okay, please.
Could you take
Yes,
the questions,
sir.
please?
So we've got huge participations from students. So I'm sure they'll benefit from your talk. So the first question, which material is commonly used in marine applications?
Yeah, like if it's well, what I have such given here, it's a copper-based alloys, but a lot of other alloys are being used also. If you look into stainless steel, a lot of varieties there, or cobalt-based alloys, nickel chrome, or copper copper nickel. There are two, depending on the application, because in the marine environment, you have to look at the role of pH, the role of the seasonality also, because like the temperature changes, the biofouling, and all those aspects you have to look, and plus the any bacterial microbiological corrosion is also there, those things. But there are a lot of alloys, but depending on particular your application, you have to see. But I can tell you, not only the copper-based alloys, the stainless steel is being also used. If you look at our pumps, mostly made of steel, steel-based stainless steel materials, and there is no, you cannot absolutely control the corrosion. So we go for a different application and the different flow requirement also. We choose the different materials.
Okay.
This particular alloy which I used, it's a propeller-based metal. Propeller for naval application of the submarines of the ship. To make the propellers, they use this material, nickel, aluminum, bronze.
Okay. The next question one of our participants is asking is, what is HVOF coating?
Oh, this is actually the name. The full form is, you have to check it. If he's a student, I think he should find himself. It is called high velocity oxyfueling process. It is a coating process, and the entire the aim of the this was being done. We took a base metal, a mild steel, and on that I made the powder of this nickel aluminum bronze. Because sometimes you can, like if you want to have like a few centimeters or few inches of thickness of a propeller, it is a very cost, economical. It is a too much. So in order to avoid that, what they're trying to do, we take a cheap substrate like a mild steel. On the top of that, we may give some coating of 200 to 300 microns of coating. But that is a. But what I would suggest is HPOP is a very good process. Like it's a plating. It's like a coating process actually. High velocity oxyfueling process. You use a very diamond shape, what we call diamond shape gun, and you spray all these metal oxide particles on the substrate at high temperature, and you achieve that coating. And I'm sure a student, he should search and find out.
Sure. Which factors are crack initiator in HVOF NAB coating?
Yeah, that is a good question. Actually, porosity is one of the factors. If it is not a good coating, that will be the initial point, because that creates a inter-networking connection between your base substrate and the top surface. That is a porosity you have to see, and also the unmelted particles. Because these particles, what I said, it's a you are melting and coating. if there is any, so you have to optimize it. That's what I was concluding in my talk. The optimization of the coating is must. So you have to make sure there are no unmetal particle, no splats on the surface, and the adherence also should be good on the substrate.
Okay. Another question. In which applications HBOF NAB coating refurbishment is viable in marine applications?
Yeah, this is what actually my work was, that I told you. It is for, like, you can, there are some other application I think now going on for valve and other things, but this was a propeller actually, propulsion system.
Okay. So we'll take the last question. Which material performs good at low kinetic energy?
That one, if you look at my data, the same material also behaves at a low kinetic energy. But here I have compared with only copper-based Alethe. I have compared with all 3.1 meter per second to 6 meter per second, 6.7 meter per second. The same material also behaves, but that is also your, you have a critical velocity for a component. If you are going for a component which will be operating at 25 meter per second, you cannot do that. If you are passing some liquid through a, for drinking water, maybe low velocity, in that case you can choose. But this same material can also work in low velocity, but you can compare with a different material depending on your application.
Okay. Thank you so much, sir, for being patient with all our questions and, of course, for your presentation. Thank you, sir.
Thank you. Thank you all. Thank you to Pincon. Thank you.
Our next speaker for marine corrosion is from Indian Maritime University, Kolkata campus, Dr. Arun K. Ishwara. He is a marine engineer, MEO Class 1, FGN professional competency, and a PhD scholar. His area of specialization include LNG containment, marine system design, thermodynamics, and mass transfer.
He has been awarded the Best Technical Paper, an award given by the Governor of West Bengal. He is going to present a paper on suggestions for improvement in marine pipeline technical tendering, an analysis on pre-pandemic tenders for improving quality and minimizing costs. Dr. Ishwara, please.
Good day, welcome to Pipeline Integrity Conference. I am Arun Kishore Ishwara. I am here to speak on the topic of marine corrosion, covering certain suggestions for improvement in pipeline technical tendering analysis on pre-pandemic tenders and for improving quality and for minimizing costs. The objective of my presentation is to improve pipeline quality, ease of workflow in pipeline projects, marine pipeline projects especially, reduce the costs, can say the capital cost, also the operation and maintenance costs. How I would be achieving the objectives is some structured, say, analysis on the tenders which I have gone through. So first I would like to explain you what is the post-COVID scenario, then current Indian oil and gas pipeline infrastructure and projects overview. Then I would speak about maritime pipeline projects, say design considerations, how the workflow is made for pipeline projects, that is during installation and commissioning. Then what are those pipeline project work difficulties I would like to bring out. Then I would suggest for improvements in the current scenario. In the post-COVID scenario, you would have increased bottlenecks in the logistics, increased push for self-reliance, protectionism from the government will be there, funds will be drying up with both government as well as the public sector undertaking units. Accelerated shift to renewable energy is there, and it will be much more taken proactively in this scenario. We will see reduce the infrastructure investment in oil and gas. And also you would see that increase the e-commerce will be there. All these factors would contribute to encouraging, say, electric power generation and reduce the retail utility of these oil and gas resources. So we would see a requirement coming up in localized areas, large demand, and reduce overall retailing costs or say demand. That is how we can visualize what is post-COVID scenario. So the research funding will be minimized. Then at the same time, we have to improve our quality and the workflow to consolidate whatever resources we have with us. So the current Indian oil and gas pipeline infrastructure, if you look at the public sector undertaking oil companies such as IOCL, HPCL, they operate large networks of pipelines. They are also new ports and industrial demand, which I listed in the previous slide. They will be there. Bulk consumers will be cropping up to meet the increased electric power generation. Then upgradation and replacing aging infrastructure will be there. Presently, PSU oil companies for the new projects, each oil company works independently on their own. Seldom these oil companies maintain their own design and project management teams. Most of the capital and maintenance costs or works are outsourced. So PSUs, they don't have dedicated, say, specialists for implementing maritime pipeline projects. They entrust the works to such specialized bodies such as Engineers India Limited or such firms which do the complete project, right from planning, executing, monitoring, controlling, everything. All the work is done by contracting firms. So when such firms are there, what do the how do the Indian energy companies work with them? Basically, they act as owners, and for meeting their requirements, they are entrusting the works to specialized companies. Now, these specialized companies also have to be identified in a proper way, following, say, the norms laid out by the financial rules and the procurement of goods and services. So there is a common mode of finding a specialized entity also through tendering, and also the firm which is identified, it carries out the complete project installation, right from material supply, surveys, everything is done through tendering, open tendering at each and every stage. This is the requirement of public sector undertaking companies. So we have this particular channel is a key for implementing pipeline projects. So I'm trying to concentrate in this area. If you look at the pipeline scenario, you will find that the pipelines, they are basically can be classified into 4 or more categories. They are primarily to do with, say, what is the product that is flowing through the pipeline. That is the decisive thing to define this classification. Why do we do so? Because usually we have control on maintenance parameters, we have control on the pipeline infrastructure, but we don't have control on the product. So depending on that variability, pipelines are classified into number of ways. But what is the key pipeline where the demand is there in future is the class of pipeline that is coming under 4 loading and unloading pipelines. You would need, you say, to supply the bulk consumers in India, and the land route is often not feasible due to problems with the land acquiring and such things. So the easiest route would be marine pipeline, and with say you can introduce certain landfall points suitably and connect these bulk suppliers. And the design considerations, they are very elaborate. Marine pipeline project is highly complex because of the marine environment. You have to have a thorough understanding of the environment, ecosystem, the environment protection, then overall cost, how the pipelines are implemented. It is altogether a very complex project for implementation. So the design specs can be prepared after elaborate study, and they can be specified in the tender documents, because I told you that we will be specifying everything through documents, written documents. So the current practices are that the PSUs list out elaborate requirements, their own requirements are running into 700 pages or even exceeding that. It's highly complex operation. So PSUs want to take control of each and every parameter. In doing so, I find that it has become increasingly complex. The complex tender will lead to increased costs. It will lead to ambiguity with the contractor finalized, because ultimately the engineers have to work with the technical specs. When we refer to so many standards in our tendering and we cite our own specifications, which are in addition to the specifications laid out by the international, say the industry, we will have difficulty with testing, procurement, increased cost for monitoring. All such things will come into picture. So apart from the design considerations which can be specified, corrosion protection is one of the key elements in a marine pipeline environment because of the corrosive environment. It can be specified in a number of ways, like raw material quality, extent of testing, pipeline fabrication, packing, handling, where you are stocking, how it is being transported, workmanship, geotechnical and hydrodynamic issues, everything you can consider. But there is more to it. That is due to the complexity of the pipeline laying. Usually, this corrosion protection, it can be specified for external, internal in the tender docs. That is what we see most of the time. Externally, coating and current cathodic protection system is being specified. Internal corrosion is highly variable that I have listed. But overall, if you look at the project flow that happens in any pipeline project, it is something like this that I have listed. Initially, you identify a contractor specialist company, then the specialized company would further identify who will supply me the pipeline, who will supply me the corrosion protection equipment, who will do the coating. All such things will be specified individually, following the technical document prepared by the PSU, say in the tender. That is called technical specifications in the tender. So usually that is constantly referred to in this implementation. Now everywhere you see that 2 star marks I have provided in the flow chart where the tender documents are referred. It is in the initial bid tender technical tendering where the engineering specifications are listed with respect to design, location, layout, what are the civil, mechanical, electrical instrumentation, schedule, timelines, all such things are mentioned. And also at the time of procurement of individual items, where you have designed everything, location you have identified, layout, but when you are procuring the goods and services, you will have to further release the technical specs through inquiries, bids, or evaluation. So pipeline is a very complex job installation. It is highly variable, but we don't see it written in the technical specs often. Each ship is very highly specialized and the costs are tremendous here. This is one of the single most expensive item if you consider in a pipeline project, hiring the ships and how much time you would hire and what kind of ship you would hire, what would be the capability. And also the pipeline layout will bring in a lot of issues with it. How the crew are handling the pipelines, whether they're welding it properly. Say some of the blocks that I have identified and presented to you in front, how the pipeline project would appear, say in unloading, that is transporting from the load to the pipeline laying vessel, then how the edges are prepared, how it is welded, each segment, because you don't have the entire pipeline in one go. You have to, the manufacturing facility will supply in standard lengths. They will be supplied with say factory coated coatings with concrete for say to prevent the pipeline floating in water. So those pipelines need to be handled very carefully. How they are being lifted, when during the lifting, how the operations are being done, whether the people have taken care in handling such pipeline, not damaging, not introducing stresses, because everything is going to affect your corrosion strength for that particular pipeline. Even the edge, machining of the edges, how the welding is handled, what kind of inspection is done after the weld, what kind of pre and post treatments are being done. These are highly specialized and highly variable. So not everything can be taken care in the technical tendering, though the PSUs are making a good effort in increasing the volume, taking into detail every spec, but not everything can be specified. Moreover, once the joint is made, it has to be properly sealed to prevent water contact, seawater contact with the bare metal. And also you have to take care of various other regular corrosion issues that are common to marine pipeline segment. So it is not only a specifications on the paper, but the contractor, their crew, their say engineers, everybody has to take care in handling the products. So that is where a lot of variability is there in the costing, but it is not being specified in the tenders. So these are the areas where I'm going to address and carry out a few say comparisons where what is going wrong. If you look at the tenders, they were prepared in great detail. Everything is being covered, and moreover, they are referring to many standards. That is one big hurdle actually to implement, to understand actually the design basis or even the requirements of the company. Because the moment too many standards are cited, each standard will further refer to various other standards. So the understanding of that particular requirements become complex. This is where a lot of mistakes can be done, a lot of overestimation can be there, and say the groundsman may not get the complete clear picture actually what is being required out of their skill. So that is where one area. If you look at the pipeline international standards, we have the standard DNV STF 101, which is the primary referred standard for marine pipelines. It itself is a sufficient, self-sufficient standard because it refers to various other standards in ensuring the integrity of the pipeline, the corrosion protection, and all the design objectives. It gives overall guidance basically. And so reference to such standard is self-sufficient. Moreover, I told you that the operational difficulties are not being addressed in the tender. It cannot be addressed. So how do we overcome this difficulty is to identify a good contractor. Good contractor in the using the frameworks with financial rules or goods and procurement, it is often a very difficult job. Moreover, once you identify a contractor also, he would try to optimize his cost saving on such things such as logistics, maybe the pipeline laying vessel, he may cut down the cost by hiring a different cheaper alternatives. So ultimately, we do not have control on each and every parameter. So the entire exercise of detailing so much in the engineering technical aspects will be defeated at the end. So realizing this aspect, the oil company should look at these areas. They have to do a bit of exercise with the experts in the field who are contractors in laying out the pipelines, what are the issues which are coming. Then they have to consult their own team that is operating these pipelines, because they will be able to suggest what are the maintenance difficulties, what are the operational difficulties which are coming with the existing pipelines. They will be able to greatly enhance the pipeline integrity. They can contribute a lot. They can contribute a lot to cut down the costing also, operational cost. So when an oil company outsources everything, the in-house expertise that is there in the operation and maintenance is not received, captured. Moreover, time frames are not being, though they are being specified in some broad way, especially in pipeline laying, the hiring costs are tremendously large, especially with respect to ships, logistics, and all such cranes and all. So it requires a careful analysis to cut down costs. Every chain you have to identify. The best part I would suggest, instead of going in a very consolidated, complex way, split down the tender into various work-based, say, aspects. Certain small scope, define a small scope, then give a timeline for it. You define the activity in the timeline, then work out the cost. Each step you further analyze into blocks, individual blocks. Carry out block by block in a whole lot of workflow together. The entire pipeline project would go for the implementation in one go, but it would be split up into individual elements so that there is a very careful control of the chain, where the previous tenders were lacking. You will be able to see on the ground what is happening where the time scheduling is increasing, where the costs are increasing, we can optimize the costing there at each and every step in this way. And also, you can request the financial bids to be given in the format that is being suggested, that the work-based items that we have identified, these can be addressed very carefully, that each scope is there, each time is there. So the financial bids should be received as per costing of individual groups. So you would know, especially the PSU, the managers there will identify how much is work getting executed at what cost and what time. So they will be able to quantify the pipeline quality that is going ultimately in the location. Earlier, this was not so evident where the cost is going. If we actually ask for complete costs, without careful identification of these individual works and say the scopes that have been shown here. This is a very good project management idea. I think it should be implemented in the tendering for achieving our objectives. Moreover, the protectionism is going to last, such as DMI S&P policy, which talks about the purchase of only Indian goods, steel, iron and steel. So oil companies not only have to look at just the project, but they have to also now open their eyes towards the Indian industry. Who is manufacturing what is available, send their representatives, get a quality check, advise them on improving the quality, and improve the industry so that their project will be benefited in the long run. I think this is the way ahead in post-COVID scenario. Earlier, this exercise may be done in certain severity, but now more trust is there because of protectionism. We can't import everything from, say, other countries. And also, for, say, the utility of the PSU, the technical manpower availability is enhanced in post-COVID scenario, because you can outsource, or you can even offer technical consultancy to academic universities and institutions, or the research bodies of in India, because you see the overall availability of these people have increased now, because the research funding has gone down. So more people are available. So PSU can work on all these larger, say, scope effectively by managing them, forming work groups of specialists. This is some of the exercises. Moreover, for identification of the contractors, specialized contractors, the GFR rules may be tweaked a bit. Maybe the policy can be implemented, and it has to be in consultation with the technical team, not only left to the admin and the finance departments. The technical aspects also should come in to reduce this cost. That has to be stressed and brought out in various committees, and the top management should be convinced in this regard. So these are some of the suggestions that is what I would like to convey. Moreover, not the least, the environmental management is something very amiss in the projects. The environmental management is one of the single most important objectives for marine projects. That itself should be included in a tender scope for the entire project. So I think with this, we should be able to improve our view, because ultimately our business should not reflect dirty in the public because of, say, the renewable thrust which is on. People are looking down upon oil and gas. So we should not get the lackadaisical approach towards oil and gas for our continued prosperity. So that is one area which I would suggest for improvement. Thank you for paying attention to my presentation. If you have any questions, I'd be happy to answer them. Thank you.
Thank you so much, Dr. Ishwara, for the presentation. Hello, sir.
Yeah, good day, sir. Thank you very much for including me in your meeting. It's a tremendous effort from you at this pandemic lockdown situation. Highly laudable, actually, with such an organized professional conduct of the meeting. And thank you for giving me an opportunity to have a view on the post-COVID scenario in tendering, especially. Thank you.
Thank you so much for the compliment, sir. We have received certain questions, sir.
Yes.
I'll take them one by one, sir. You have 10 minutes in the Q&A session.
Yes.
The first question is, what are the effective controls to prevent internal corrosion?
Okay. I would say that first, internal corrosion, it has usually how do we present is about say with the wall corrosion allowance initially at the time of design. This is one such aspect. Material selection is the other one. These two are the ones which will decide for most of the lifetime. Second is the product say quality. We don't have much quality, but we can do have certain controls such as say filtering, avoiding abrasive things, particles coming in. Then possibly we can have a water separator, maybe some other few separation and processing equipments which we can have. And what I also hear in the new developments is that there are certain say coatings being used internally also. But let me share one of my practical experience at Papua New Guinea. I was involved in operation from ship to the terminal, which is a Canadian owned, I think, investment thing. They were doing such first time that the refinery has come up, and they were pumping with a newly advertised and promoted hose, which has an internal lining. Towards the end of the operation, like we were unloading naphtha, it's a very distillate grade of petroleum. We were unable to shut our ship's manifold. Then even I had to visit there, being the engineer on duty, and I was unable to even close that manifold. We could not guess what is happening. We took the ultimate risk of disconnecting the hose without shutting the manifold, closing down by valves and trying to pull it out. To our utter surprise, the entire inner lining of the hose is stuck into our manifold.
Okay.
So the specifying inner coatings is sometimes very risky. That is what I have seen in practice. So I could say that management time to time pigs are there. Intelligent pigs have come up now. A lot of instrumentation has developed. I think it is a good operational judgment and timely maintenance can save the pipeline.
Okay. The next question is, what are the main suggestions for improvement in tendering of offshore pipelines?
Okay. I have listed actually a concept which I got that would improve the tendering process. Currently, we have almost each tender reflecting a book almost on the subject. In fact, what I have seen, most of the technical tenders which are floated, they exceed even any book, standard book you have on the subject. It is such informative. So if I am the contractor, if I want to pick up the job, I will break my head actually, getting into the nitty-gritties and tracing each and every standard. It is a highly complex thing. Then how do? I overestimate everything. Okay, ASME code is there, my DNV standard is there, NACE code is there, everything is there. I will increase all the costing. Okay, I have to fulfill this, I have to fulfill this. Somehow I have to meet the technical specification, otherwise I will be disqualified. I will not even go for the financial bit. So to meet, I would enhance. These are all overestimations. And moreover, as I have listed, that what is exactly installed in place is the one that is going to speak for its life, not what is on the paper. We may fulfill all the technical specs, but ultimately, if it is a bad workmanship, it will fail on the first operation only. So, realizing this, what I am suggesting that follow one particular standard. If the offshore tendering is there, the well-established DNV ST101F, use that only. If you even go through an exercise of the DNV standard, you will find actually individual blocks. Structure your tender document so as to reflect the standard itself. Don't go anywhere. Second, what I would like to say is, create now a work-based scheme. What is individual work I can define? What is the first block I can define? How much time, how much cost? Ask the contractors to fulfill that quote as per each block item. Once the block is there, PSUs are they are comfortable now. they know the work is done, they can release the payment. The contractor will not suffer because of timely payments. The cash flow will be there. He will be able to continue with the network. Next work step. It is a win-win for both the PSU as well as the contractor in such cases. And other part which I am trying to say, the environmental management, which is a highly risk. It's a high risk these days. With maybe one tweet or the other, the entire projects get defeated. The cost may escalate. You have to face a lot of action. So what I mean, keep environmental management also included in the tender to avoid any escalation of issues. Put that very clearly, who is going to do what, how they are going to be managed. Even for the, say, post testing, that is one major area where the pipeline has to be flooded with water, and certain additives are made there because seawater is being admitted, so you have to maintain some quality for the water. Otherwise, it is going to eat your pipeline. So how do you dispose this volume of water? Maybe it may be some maybe 50 or 100 kilometers pipeline filled with the seawater. You can see with additives. How do you dispose this water? If somebody even questions, how do you manage the cost? Tender document doesn't speak. Then you have to look at ways how to address such issues. So don't get into such kind of situations, especially in post-COVID, which will escalate your project costing. As such, we have very limited funding available. Try to use it wisely. I cannot suggest in this limited time because the offshore pipeline itself is a very complex job. Maybe in a holistic way we can work. Even I have some suggestions. I can improve some flows, workflows, which I'm not be able to express everything right now. But I'm open to for any contact or say working with oil companies.
Sure, sir. One last quick question, sir. Could you explain what corrosion fatigue is?
Okay. With fatigue, the word fatigue is used when things are the design parameters are complied. Like for example, if you take stress, where fatigue is discussed, the stresses, allowable stresses are not exceeded, but due to cycling, usually the materials will fail. This is a well-known phenomena with materials. If you look at the offshore pipeline, what are such fatigues? What are the cyclical things? Especially if you look at it, it is not a fixed installation. You can say, though you may think that okay, my pipeline is fixed, but the ships which are coming there are not fixed assets. Each ship is a different. It has a different plant. It has a different pump. It has a different pumping characteristics. Each operation is different. It is not the same. So what you are going to ultimately have is cyclical loadings. The cyclicals you cannot avoid. Moreover, if you are doing say pigging operations, you are include whatever you do, it is changing some cycle. So with that, your corrosion resistance, though you have accounted and well within the limits, it may fail prematurely at a point where it is getting the maximum repeated cycles.
Right, so thank you so much for joining us and taking time out of your schedule. It was really nice talking to you, sir, and having you over at Pincon. Thank you, sir.
Thank you, sir. Thank you very much.
Thank you.
Good day.
Bye-bye. We have received a message from our technical team also. You all will be glad to know that we had record numbers at the exhibition yesterday, peaking at 2,500 in the lobby area. We had almost 1,500 visits at the sponsors zone, around 400 at the exhibitors zone. The inauguration and technical symposia was attended by a peak 250 visitors yesterday, despite all the technical issues we faced. We are thankful to all of you for joining us today, and we hope you have a great time at Pincon.
And now it's time for a 40-minute lunch break. Enjoy your food along with networking with the sponsors and exhibitors. We shall be starting with the symposia on corrosion monitoring and mitigation in CGD.
Thank you.